Hello there, and welcome back to Science to Fall Asleep. Tonight, there is nothing to solve, nowhere to rush, and nothing expected of you except to become comfortable. Perhaps your room is quiet. Perhaps rain is gently tapping against the window, or the world outside has already settled into silence. However your evening sounds, allow them to fade gently into the background as we leave Earth behind for a while. Take one slow breath in and let it go. As your breathing becomes softer, imagine yourself drifting upward through the night sky, leaving behind busy streets, glowing cities, and the worries of another day. The stars slowly become brighter. The darkness becomes peaceful rather than empty. Above you stretches the greatest story ever written, a story that has been unfolding for nearly 14 billion years. Tonight, we'll wander through that story together, not as students preparing for an exam, not as scientists searching for answers, but as quiet travelers exploring the universe, one gentle thought at a time. We'll float among ancient starlight that has traveled millions of years simply to reach your eyes. We'll visit invisible clouds where stars are quietly being born. We'll drift beside galaxies so enormous that even light needs hundreds of thousands of years to cross them. We'll explore black holes, mysterious particles, silent planets, glowing nebulae, and the invisible fabric of space itself. The wonderful thing about astrophysics is that it asks questions so enormous they make our everyday worries feel wonderfully small. How did the universe begin? Why do stars shine? What is hidden inside a black hole? Could there be other worlds where someone else looks up into their own quiet night? No one knows every answer. And somehow, that makes the universe even more beautiful. As we travel together tonight, you don't need to remember every detail. In fact, forgetting is perfectly welcome. If your thoughts drift away, simply let them. If sleep arrives halfway through our journey, that's exactly what this channel is here for. There will be no sudden surprises, no loud interruptions, only calm discoveries told slowly enough that your imagination can gently wander beside them. By the time this journey is over, we'll have crossed billions of light years without ever leaving your pillow. We'll watch stars being born from cold clouds of cosmic dust. We'll witness the peaceful lives of giant galaxies slowly dancing around one another. We'll visit strange objects where gravity bends both light and time. We'll explore the quiet mathematics hidden inside the universe. We'll discover why empty space isn't truly empty. We'll wonder about invisible matter that quietly shapes entire galaxies. And we'll finish our journey gazing into the deepest darkness ever observed by humanity, where the oldest light still whispers stories from the beginning of everything. Each discovery will gently lead into the next, like turning pages in a bedtime story written across the entire universe. So whether you've loved astronomy your whole life, or tonight is the very first time you've ever thought about astrophysics, you're in exactly the right place. Before we begin our long journey among the stars, I have one small favor to ask. If these relaxing science stories help you unwind after a long day, consider taking just a moment to like this video and subscribe to the channel. It truly helps more curious minds discover these peaceful journeys through science. Now, dim the lights if you haven't already. Settle into your favorite sleeping position. Let your shoulders become heavy. Relax your jaw. Allow your breathing to find its own comfortable rhythm. Imagine the stars above shining quietly, patiently waiting for us. There is no countdown, no destination, only an endless universe waiting to tell its story. And our story begins with something so small that it almost seems impossible. A tiny spark, a moment smaller than imagination itself. A beginning from which every star, every galaxy, every planet, every ocean, every mountain, every living creature, and eventually you, would quietly emerge. So close your eyes, take another slow, peaceful breath, and let's gently drift into the relaxing story of astrophysics together. Long before there were stars sparkling across the darkness, before galaxies stretched through space, before planets circled distant suns, the universe was unimaginably different. There were no familiar shapes to recognize, no colors, no sounds, and no places that could have been called home. Yet within that extraordinary simplicity rested the possibility of everything that would ever exist. Astrophysicists spend their lives trying to understand those earliest moments. It is a remarkable idea that by studying faint light from the deepest reaches of space, humanity can slowly reconstruct events that happened nearly 14 billion years ago. Like detectives examining ancient footprints, scientists gather tiny clues scattered throughout the cosmos, allowing us to piece together a story written across both space and time. The beginning of a universe is often called the Big Bang, although the name can be slightly misleading. It wasn't an explosion that happened somewhere inside empty space. Instead, space itself began expanding. Every direction, every future galaxy, every distant star, and every atom that would eventually become part of our world all emerged together as the universe itself unfolded. Imagine drawing tiny dots on the surface of a balloon. As the balloon slowly inflates, every dot moves farther away from every other dot. None of the dots sits at the true center of the expansion because the entire surface grows at once. Astrophysicists often use this simple picture to help explain how our universe expands, though the real universe is far more mysterious and far more beautiful. In those first tiny fractions of a second, the universe was so incredibly hot that nothing familiar could exist. Temperatures were beyond anything found inside, even the hottest stars today. Matter and energy blended together in ways that challenge our everyday understanding. Tiny particles flashed into existence and disappeared almost instantly, filling the newborn cosmos with constant motion. As the universe continued expanding, something peaceful began to happen. Expansion caused everything to cool. Little by little, the unimaginable heat faded, like steam slowly drifting away from a warm cup of tea on a quiet evening. The universe became calmer with every passing moment. Cooling allowed the first stable particles to survive. These tiny building blocks would eventually become the atoms that form stars, oceans, trees, mountains, and even the cells inside your own body. Every breath you take today contains atoms whose story began during those incredibly early moments of cosmic history. One of the most comforting ideas in astrophysics is that nothing in the universe is truly separate from its beginning. Every galaxy still carries ancient memories of those first moments. Every star quietly preserves pieces of that original story. Even the calcium inside your bones and the iron flowing through your blood are chapters of a tale that started billions of years before Earth even existed. As the universe reached only a few minutes of age, another important milestone quietly arrived. Protons and neutrons combined to create the first simple atomic nuclei. Most became hydrogen, while some became helium. These two elements would dominate the young universe, patiently waiting for gravity to begin its slow and gentle work. Then came a surprisingly long period without stars. For hundreds of millions of years, the universe remained dark. Not frighteningly dark, simply peaceful. Imagine floating through an endless sea of invisible hydrogen, where no sunlight yet shines because no stars have awakened. The universe rested in quiet anticipation, holding all the ingredients needed for countless future galaxies, but not yet arranged into the magnificent structures we know today. Gravity, however, is wonderfully patient. Unlike storms or explosions, gravity rarely rushes. It gently gathers tiny amounts of matter together over immense periods of time. Small differences in density slowly became larger. Slightly crowded regions attracted more gas, which attracted even more gas, beginning a process that would eventually ignite the first stars. This gradual transformation reminds us that some of the greatest changes in nature happen almost too slowly to notice. Astrophysics often teaches that the universe prefers patience over speed. Entire galaxies evolve over billions of years. Stars spend millions of years preparing to shine, and even the largest structures in existence are built through countless tiny steps rather than sudden events. Eventually, somewhere within those growing clouds of hydrogen, gravity compressed gas tightly enough for nuclear fusion to begin. The first stars quietly lit the darkness, ending what astronomers sometimes call the cosmic dark ages. Their light spread across the expanding universe, illuminating space for the very first time. Those first stars were unlike many we see today. They were enormous, brilliant, and short-lived, burning with incredible intensity. They transformed simple hydrogen into heavier elements that had never existed before. Carbon, oxygen, silicon, and many of the ingredients needed for future planets slowly began to appear inside their blazing cores. When those ancient giants reached the end of their lives, many exploded as spectacular supernovae, scattering their newly created elements across space. Although the explosions themselves were unimaginably powerful, they also represented new beginnings. Their ashes became the raw material from which future generations of stars, planets, and eventually life itself would form. Every time astrophysicists study distant galaxies, they're also looking backward through time. Because light travels at a finite speed, the farther away an object is, the longer its light has traveled before reaching Earth. Looking at galaxies billions of light years away allows us to witness the universe as it appeared billions of years ago. In a sense, every telescope is a time machine, not because it changes time, but because it patiently collects ancient light that has spent unimaginable ages crossing the universe just to arrive at our eyes tonight. That simple realization makes every star above seem even more extraordinary. Some of the light shining gently through Earth's night sky tonight may have begun its journey before human civilization existed. Other lights started traveling long before dinosaurs disappeared. Some photons have crossed nearly the entire observable universe simply to end their journey inside a telescope, or perhaps inside your own eyes. The deeper astrophysics explores the universe, the more it reveals that time and space are woven together into one magnificent story. Every observation becomes a quiet conversation with the distant past, reminding us that the night sky is not merely a collection of stars. It is history itself, still glowing softly across the darkness. And as the first stars continued illuminating the young universe, something even grander slowly began to emerge. Entire galaxies were preparing to take shape, each becoming a city of billions of suns drifting gracefully through the endless cosmic ocean. As the first generations of stars quietly filled the universe with light, gravity continued its patient work. It had no hurry, no grand announcement, and no sudden leap forward. Instead, over hundreds of millions of years, countless stars slowly gathered into enormous families. These families would become the galaxies we admire today. Vast islands of light scattered across an ocean of darkness. If you could somehow watch the universe and fast forward, billions of years would pass like gentle ripples across a calm lake. Small clouds of gas would drift together, merge, and slowly grow. Tiny collections of stars would become larger ones. Gravity would quietly shape them all, never stopping, never resting, always guiding matter toward new patterns. Our own home, the Milky Way, is just one of these immense star cities. It contains hundreds of billions of stars, along with clouds of gas, ribbons of dust, mysterious dark matter, and perhaps trillions of planets. Yet despite its incredible size, it is only one galaxy among hundreds of billions that astronomers believe fill the observable universe. Imagine standing on a quiet beach at night, looking across an endless sea. Each distant lighthouse represents an entire galaxy. Now imagine that every lighthouse is not a single light at all, but hundreds of billions of glowing suns gathered together. That comparison still falls short, because the universe stretches far beyond anything our minds naturally picture. One of the most elegant discoveries in astrophysics is that galaxies come in many beautiful shapes. Some resemble graceful pinwheels, their spiral arms gently wrapping around bright centers. Others appear smooth and rounded, glowing like enormous golden lanterns. Some look irregular, as though gravity painted them freely without following any familiar design. These shapes are not random. They tell stories that stretch across billions of years. A spiral galaxy often reveals a peaceful history, where stars have quietly orbited their center for immense periods of time. An elliptical galaxy may have formed after ancient collisions, when two or more galaxies slowly merged into one larger home for countless stars. Every curve, every stream of light, and every cloud of dust records another chapter in a galaxy's remarkable life. Our Milky Way is itself a spiral galaxy. From Earth, we cannot step outside to admire its full shape because we live safely within one of its spiral arms. It is a little like trying to understand the shape of an entire forest while standing among the trees. We see countless individual stars around us, yet the grand design only becomes clear when astronomers compare our observations with those of distant galaxies. At the very center of the Milky Way lies one of the most fascinating objects in astrophysics, a supermassive black hole. Although it contains millions of times the mass of our Sun, it occupies an astonishingly small region compared with the enormous galaxy surrounding it. Yet its gravity quietly helps shape the motions of nearby stars, reminding us that even invisible objects can influence an entire cosmic neighborhood. Surrounding the galactic center, stars travel along gentle orbits that take millions of years to complete. Our own Sun is one of them. At this very moment, as you rest comfortably listening to this story, the entire solar system is moving around the center of the Milky Way at roughly 220 kilometers every second. That sounds unimaginably fast. Yet because everything around us moves together, we feel nothing at all. In fact, since the dinosaurs disappeared from Earth around 66 million years ago, our solar system has not even completed a single full orbit around the galaxy. One galactic year, the time needed for the Sun to circle the Milky Way once, lasts about 225 million Earth years. Astrophysics often reminds us that the clocks of the universe tick very differently from the clocks we use every day. A human lifetime may seem long from our perspective, but compared with galaxies, it is only a gentle heartbeat. Stars are constantly being born throughout the Milky Way. Hidden inside enormous molecular clouds, gravity slowly gathers cold hydrogen gas into denser and denser regions. As these clouds collapse, their centers become warmer until nuclear fusion finally begins. A new star quietly opens its eyes to the universe. Nearby, older stars slowly grow old. Some gently shed their outer layers into space, creating delicate glowing shells that astronomers call planetary nebulae. Others, much larger than our Sun, end their lives in magnificent supernova explosions, briefly shining brighter than entire galaxies before fading away. Nothing is wasted. The material released by dying stars becomes the raw ingredients for future generations of stars and planets. The oxygen we breathe, the carbon in every living cell, the calcium inside our bones, and the iron carried through our blood were all forged inside stars that lived and died billions of years before the Earth was born. Carl Sagan once expressed this beautifully by saying that we are made of star stuff. Modern astrophysics continues to support that poetic truth. Every atom heavier than hydrogen and helium has traveled through ancient stellar furnaces before eventually becoming part of our world. Perhaps that is one of the most comforting ideas in science. The universe is not something separate from us. We are one small chapter within its endless story. When you look at the night sky, you are not gazing at something completely distant. In a quiet way, you're looking at your own ancient family history, a history written across billions of years and countless generations of stars. Galaxies themselves are never completely still. They drift through space, gently pulled by one another's gravity. Sometimes two galaxies pass close together, stretching graceful streams of stars across the darkness like glowing ribbons. Other times they slowly merge, their billions of stars weaving together over millions of years to create an entirely new galaxy. Although the word collision may sound dramatic, the stars inside those galaxies are so incredibly far apart that direct crashes between individual stars are exceedingly rare. Instead, gravity carefully rearranges their paths, creating new shapes that will remain for billions of years. Our own Milky Way is slowly approaching the neighboring Andromeda Galaxy. The journey is so gradual that it will take roughly 4 to 5 billion years before the two galaxies begin their graceful merger. Long before that distant future arrives, the Sun itself will have changed dramatically, reminding us once again that the universe always moves according to timescales far beyond ordinary experience. Looking deeper into space, astronomers have discovered clusters containing hundreds or even thousands of galaxies bound together by gravity. Beyond those clusters lie enormous filaments stretching across the observable universe, forming what scientists call the cosmic web. From the largest perspective we can imagine, galaxies resemble tiny droplets of light connected by invisible threads across unimaginable distances. Between those glowing strands are immense regions where almost no galaxies exist at all, creating vast cosmic voids that span hundreds of millions of light years. It is astonishing that the universe can be both incredibly crowded and wonderfully empty at the same time. This delicate balance between matter and emptiness gives the cosmos its breathtaking structure, allowing gravity to sculpt patterns so immense that even the largest galaxy becomes only a small piece of a far greater design. And among all those galaxies, all those stars, and all those quiet rivers of light flowing through space, tiny worlds begin to appear. Planets circling distant suns, each carrying its own silent story, patiently waiting for us to explore. As galaxies matured and stars settled into their long, graceful lives, something remarkable began happening around many of them. Tiny grains of dust and clouds of gas, left behind after a star's birth, continued circling their brilliant parent. These quiet disks, almost invisible against the vast darkness, would slowly become the birthplace of planets. There was no master architect arranging them into perfect order. There were only the gentle laws of physics, patiently guiding countless tiny particles through millions of years. Imagine floating above one of these newborn stars. Around it stretches a broad, glowing disk made of dust finer than flour, crystals smaller than grains of sand, frozen ice, and swirling gases. At first glance, it might seem chaotic, but hidden within that gentle motion is a quiet rhythm. Every orbit, every collision, and every tiny movement slowly contributes to building entirely new worlds. Dust grains lightly touch one another. Some stick together, others drift apart. Then those tiny clusters meet more particles, gradually becoming pebbles. Pebbles become rocks. Rocks become mountain-sized bodies. Over millions of years, gravity takes over once again, drawing these growing worlds together until planets slowly emerge from the cosmic dust. Astrophysicists sometimes describe this process as nature building with extraordinary patience. Nothing appears overnight. Every planet, from the smallest rocky world to the largest gas giant, is the result of countless small events quietly unfolding over immense stretches of time. Our own solar system followed this peaceful path about 4.6 billion years ago, long before Earth had oceans or forests, before the moon illuminated the night sky, before the first living cell quietly appeared. There was simply a young sun surrounded by a spinning cloud of gas and dust. Piece by piece, the familiar planets we know today slowly took shape. Closest to the sun formed Mercury, a small rocky world whose days are hotter than many ovens, while its nights become colder than the coldest places on Earth. Without much atmosphere to protect it, Mercury experiences some of the greatest temperature changes anywhere in the solar system. Farther outward formed Venus, wrapped beneath thick clouds that hide its surface from ordinary view. Beneath those clouds lies a landscape so hot that lead could melt upon its rocky plains. Although Venus and Earth are nearly the same size, their histories became astonishingly different. Then came Earth, not immediately the blue planet we know today. At first, it was a restless world covered in molten rock. Volcanoes erupted across its surface, while countless asteroids still wandered through the young solar system. Slowly, as millions of years passed, the surface cooled. Water collected. Oceans formed. The atmosphere gradually changed. Eventually, in ways scientists continue to study, life quietly appeared. Astrophysics often reminds us that our existence depends upon an extraordinary chain of events stretching back billions of years. If even one chapter had unfolded differently, our world might never have become the peaceful home we know today. Beyond Earth lies Mars, a planet that still captures human imagination. Dry river valleys, ancient lake beds, and minerals formed in water all suggest that Mars was once a wetter place. Billions of years ago, it may have looked surprisingly different from the cold desert we observe today. Even now, robotic explorers patiently examine its surface, searching for clues hidden among its rocks. Every discovery teaches us not only about Mars, but also about the early history of Earth itself. Far beyond the rocky planets stand the giants. Jupiter, the largest planet in our solar system, contains more than twice the mass of all the other planets combined. Its swirling clouds create patterns that have lasted for centuries, while its famous Great Red Spot is a storm so enormous that several Earths could fit comfortably inside it. Despite its immense size, Jupiter never became a star. It simply lacked enough mass to ignite the sustained nuclear fusion that allows stars to shine. Instead, it remains a magnificent giant, quietly ruling the outer solar system with its powerful gravity. Nearby drifts Saturn, surrounded by perhaps the most elegant rings in the solar system. From a distance, they appear solid and smooth. Yet astrophysicists know they are made of countless pieces of ice and rock, each following its own peaceful orbit around the planet. If you could somehow stand safely among Saturn's rings, you would not see a giant, continuous band. Instead, you would find billions upon billions of icy fragments, many separated by surprisingly large distances, glimmering gently beneath distant sunlight. Farther still lie Uranus and Neptune, often called the ice giants. Their deep blue colors come from methane in their atmospheres, while powerful winds race across their cloud tops at astonishing speeds. Neptune, despite receiving only a tiny fraction of the sunlight that reaches Earth, hosts some of the fastest winds ever measured anywhere in the solar system. Yet our solar system is only one tiny example among an almost unimaginable number. For thousands of years, humanity wondered whether other stars might also have planets. Today, astrophysicists no longer wonder. They know. Using powerful telescopes, scientists have discovered thousands of exoplanets orbiting distant stars. Some are scorching worlds where temperatures melt rock. Others are frozen planets wandering far from their suns. Some are larger than Jupiter, while others are only slightly bigger than Earth. Each discovery expands our imagination a little further. Some exoplanets complete an orbit in only a few days. Others take centuries. Some circle two stars instead of one, where sunsets might glow beneath twin suns crossing the sky together. Others drift freely through the darkness with no parent star at all, wandering between galaxies as lonely rogue planets. These distant worlds remind us that nature enjoys extraordinary variety. The universe rarely repeats itself exactly. Every planetary system carries its own history, shaped by gravity, time, and countless small events that unfolded long before any observer arrived. Perhaps somewhere among those distant planets, rain falls beneath unfamiliar clouds. Perhaps mountains rise beneath orange skies. Perhaps frozen oceans reflect the light of red dwarf stars. Or perhaps those worlds remain completely silent, beautiful simply because they exist. Astrophysics encourages both curiosity and humility. Every new telescope reveals planets we never imagined. Every mission uncovers landscapes unlike anything on Earth. And every discovery gently reminds us that our own world, precious though it is, represents only one page in an unimaginably large cosmic library. As astronomers continue searching the skies, one question quietly follows every observation. Could life exist elsewhere? It is a question that has inspired dreamers, scientists, philosophers, and storytellers for generations. The answer remains unknown, but the search itself has transformed the way we see our place in the universe. And to continue that search, astrophysicists must learn to read one of the universe's most mysterious messengers, light itself. For every color shining from a distant star carries a hidden story, waiting patiently to be understood. Light is so familiar that we rarely stop to think about how extraordinary it truly is. Every morning, sunlight gently slips through windows, warming the earth without asking for attention. Every evening, the stars quietly decorate the darkness, sending their ancient glow across unimaginable distances. Yet astrophysics has revealed that light is far more than something we simply see. It is the universe's greatest storyteller. Unlike planets or stars, astronomers cannot travel to distant galaxies to collect samples with their hands. Even the nearest star beyond our sun is more than 4 light years away, a distance so vast that our fastest spacecraft would need tens of thousands of years to reach it. Instead, scientists patiently wait. They allow light to come to them. Every tiny beam arriving at a telescope carries information about where it has been, what created it, and the incredible journey it has completed across space. Learning to read that information is one of the greatest achievements in astrophysics. Imagine receiving a handwritten letter from someone who lives impossibly far away. The paper tells you not only what they wish to say, but also something about the ink, the handwriting, the weather it traveled through, and even how old it is. Light behaves in much the same way. Every photon, the smallest packet of light, quietly carries clues about its source. Hidden within its color, brightness, and energy is a remarkable amount of information waiting to be discovered. The word photon may sound mysterious, but its journey is beautifully simple. A photon born deep inside the sun begins in an incredibly crowded place. At the sun's core, temperatures reach nearly 15 million degrees Celsius, and atoms are packed tightly together. There, nuclear fusion releases enormous amounts of energy, creating countless photons every second. Surprisingly, those newborn photons do not race directly into space. Instead, they spend an astonishingly long time bouncing from one particle to another inside the dense interior of the sun. Each collision changes their direction, forward, backward, sideways, over and over again. Some astrophysicists estimate that a single photon may wander inside the sun for hundreds of thousands of years before finally escaping its surface. Once it reaches space, everything changes. The journey that took hundreds of thousands of years inside the sun is followed by only about 8 minutes traveling across the empty space between the sun and Earth. 8 peaceful minutes. Then that same photon might gently land upon a leaf, warm your face during a quiet afternoon, or perhaps enter a telescope pointed toward the heavens. It is remarkable to think that the sunlight touching your skin today began its story long before human history was recorded. Light also behaves in ways that seem almost magical. Sometimes it acts like a wave, spreading smoothly across space, much like gentle ripples moving across a calm lake. At other times, it behaves like tiny individual particles called photons. This strange dual nature puzzled scientists for generations. Even today, it reminds us that the universe does not always follow the simple expectations of everyday life. Astrophysics embraces these mysteries rather than fearing them. Instead of asking why nature refuses to fit neatly into our intuition, scientists patiently observe, measure, and learn for what the universe quietly reveals. Visible light, the rainbow of colors our eyes can detect, is only a tiny portion of a much larger family known as the electromagnetic spectrum. Beyond red lies infrared light, carrying gentle warmth. Beyond violet lies ultraviolet light, energetic enough to cause sunburn. Farther still are X-rays and gamma rays, born in some of the most violent places in the cosmos. On the opposite end stretch radio waves, with wavelengths so long they can span entire buildings or even mountains. To the universe, these are all simply different forms of light. Our eyes happen to notice only a very small window. This realization is wonderfully humbling. Imagine listening to a magnificent orchestra while hearing only a few instruments. The melody would still be beautiful, but much of the performance would remain hidden. That is how humans naturally experience the universe. Fortunately, astrophysicists have learned to build remarkable instruments capable of hearing the rest of nature's orchestra. Radio telescopes reveal enormous clouds of cold hydrogen drifting quietly between the stars. Infrared telescopes peer through thick curtains of cosmic dust, uncovering newborn stars still hidden inside their stellar nurseries. X-ray observatories capture the glowing remains of exploding stars and the fierce environments surrounding black holes. Gamma-ray telescopes detect astonishing bursts of energy arriving from galaxies billions of light years away. Each telescope shows the universe wearing a different face. Together, they create one breathtaking portrait. Perhaps one of the most beautiful discoveries involving light is something known as spectroscopy. At first glance, starlight appears perfectly white. Yet when that light passes through a special instrument called a spectroscope, it spreads into a rainbow of colors. Hidden among those colors are tiny dark lines, almost like fingerprints. Every chemical element produces its own unique pattern. Hydrogen leaves one set of lines. Helium creates another. Iron, calcium, oxygen, carbon, sodium. Each writes its own signature into the light. By studying these delicate patterns, astrophysicists can determine what distant stars are made of without ever touching them. It is one of science's quiet miracles. From hundreds or even thousands of light years away, a beam of light can reveal the composition of a star, its temperature, its motion, and even whether planets are orbiting around it. Light never speaks aloud. It tells astonishingly detailed stories. It also reveals motion through something called the Doppler effect. You may have already experienced this on Earth. As an ambulance approaches, its siren sounds slightly higher. As it moves away, the sound becomes lower. The same idea applies to light. When a galaxy moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light stretches toward the red. This gentle stretching, known as redshift, became one of the greatest clues in all of astrophysics. It showed astronomers that distant galaxies are moving away from one another. Not because they are racing through empty space like airplanes across the sky, but because space itself continues expanding, carrying galaxies gently apart. Every measurement of redshift quietly echoes the story of the universe's beginning. Even the faintest beam of light from the edge of the observable universe carries evidence that space has been growing larger for billions of years. It is extraordinary to think that a simple shift in color can reveal the history of the entire cosmos. Every evening, when we look upward and notice the quiet sparkle of distant stars, we are not simply seeing beautiful lights decorating the sky. We are reading messages written across millions or even billions of years. Messages carried faithfully by tiny photons that never lost their way. Messages telling us about stars that lived long before humanity existed. And among all those ancient messages, some come from places where gravity becomes so powerful that even light itself begins to struggle. Those mysterious regions, hidden within the hearts of galaxies and born from the deaths of giant stars, are among the most fascinating objects in all of astrophysics. They're known as black holes. Black holes are among the most fascinating and mysterious objects in the universe. For centuries, humans looked into the night sky and wondered about the hidden places beyond our understanding. We imagined distant worlds, unknown stars, and strange regions where the normal rules of nature might behave differently. Among all those cosmic mysteries, black holes stand apart. There are places where gravity becomes so powerful that nothing, not even light itself, can escape once it passes a certain boundary. Yet despite their dramatic reputation, black holes are not cosmic monsters wandering through space, searching for planets to consume. They are much quieter than many stories suggest. Most black holes simply exist, peacefully following the same laws of gravity that shape everything else in the universe. A black hole begins with a star. Not every star becomes one. Our sun, for example, will never become a black hole because it does not have enough mass. But the largest stars in the universe live very different lives. These giant stars are enormous furnaces, burning through their fuel at incredible speeds. They shine brilliantly, sometimes millions of times brighter than the sun, but their powerful energy comes at a cost. The more massive a star is, the faster it uses its resources. Eventually, after millions of years of creating heavier and heavier elements inside its core, the star reaches a moment when it can no longer continue producing enough energy to support itself. Gravity begins to win. The star's enormous weight pushes inward. The core collapses. In a matter of seconds, a structure that existed for millions of years can transform completely. The outer layers of the star may explode outward in a spectacular supernova, releasing incredible amounts of energy and scattering newly created elements across space. But the center can become something entirely different. If enough mass remains compressed into a tiny region, a black hole is born. It is difficult to imagine the scale of this transformation. A star much larger than our sun can collapse into an object whose center is smaller than a city, yet still contains several times the mass of our entire sun. The gravity becomes so intense because all that mass is packed into such a small area. A black hole is not empty space. It is actually a tremendous amount of matter compressed into an extraordinary state. At the heart of a black hole lies a region scientists call a singularity. According to our current understanding of physics, this is where matter becomes compressed to an extreme point where our existing theories struggle to fully describe what happens. The mathematics becomes complicated, the questions become deeper, and the universe keeps some of its secrets hidden. Surrounding the black hole is a boundary called the event horizon. This is not a physical surface like the ground of a planet or the edge of a star. It is a point of no return. Crossing the event horizon means that escaping would require traveling faster than light itself, something that the laws of physics do not allow. Outside the event horizon, a spacecraft could theoretically escape if it had enough energy and the right path. Inside it, all possible paths lead deeper inward. Time itself behaves strangely near a black hole. According to Einstein's theory of relativity, gravity affects the flow of time. The stronger the gravity, the slower time passes compared with regions farther away. This means that someone approaching a black hole would experience time differently from someone observing from a safe distance. The difference would become increasingly dramatic near the event horizon. To a distant observer, a falling object would appear to slow down as it approached the edge, its light becoming stretched and dimmer until it seemed to freeze. But for the person falling toward the black hole, their own experience would feel normal. Their clock would continue ticking. Their thoughts would continue. Their heartbeat would continue. This strange difference between perspectives reveals one of the most beautiful ideas in modern physics. Time is not a universal river flowing at the same speed everywhere. It is connected to the fabric of space itself. Black holes are often described as holes in space, but that description can be misleading. They are better understood as regions where space-time, the combination of space and time, has been dramatically curved by immense gravity. Imagine placing a heavy ball on a stretched fabric. The fabric bends downward around the weight. Smaller objects nearby would follow curved paths around that depression. The real universe is far more complex, but this simple image helps us imagine how massive objects influence the structure around them. A planet curves space-time slightly. A star curves it more. A black hole creates one of the strongest distortions known. Some black holes form from individual stars, but others are unimaginably larger. At the centers of many galaxies are supermassive black holes containing millions or even billions of times the mass of our Sun. Our own Milky Way contains one called Sagittarius A star. It sits quietly at the center of our galaxy, about 26,000 light years away from Earth. Despite its enormous mass, it does not pull every star in the galaxy directly toward it. The stars around it continue following their own paths, just as Earth continues orbiting the Sun. Gravity follows predictable rules. Distance matters. Motion matters. And the universe maintains a delicate balance. When matter gets close to a black hole, things become more dramatic. Gas and dust can spiral inward, forming a glowing disk called an accretion disk. As this material accelerates and becomes extremely hot, it can release enormous amounts of energy, sometimes shining brighter than entire galaxies. These glowing regions allow astronomers to study black holes, even though black holes themselves produce no visible light. Scientists also study black holes through their effects on nearby objects. A star moving strangely may reveal the presence of an invisible companion. A cloud of gas orbiting rapidly around a hidden region can provide clues about the mass and location of a black hole. In recent years, humanity achieved another extraordinary milestone. Scientists captured the first image of a black hole shadow. The image did not show the black hole itself, because no light can escape from inside the event horizon. Instead, it revealed the glowing material surrounding the black hole, and the dark silhouette created by its powerful gravity. It was a photograph of something that, for generations, existed only in mathematical predictions. A reminder that imagination and observation can eventually meet. Black holes also produce some of the most powerful events in the universe. When two black holes collide, they create ripples in space-time called gravitational waves. These waves travel outward at the speed of light, carrying information about events that happened billions of years ago. In 2015, scientists detected gravitational waves for the first time, confirming another prediction made by Einstein more than a century earlier. The universe had revealed a new way of communicating, not through light, but through the vibrations of space-time itself. Perhaps the most beautiful thing about black holes is that they represent both knowledge and mystery. They show us how far science has progressed, and they remind us how much remains unknown. Every answer opens another question. What truly happens beyond the event horizon? How do black holes grow? What role did they play in the formation of galaxies? Could they connect to deeper theories of the universe? These questions continue inspiring astrophysicists around the world. And while black holes may appear like places of darkness, they have helped humanity discover some of the brightest ideas ever created. They teach us about gravity. They teach us about time. They teach us about the limits of our understanding. And somewhere in the quiet darkness between galaxies, these incredible objects continue their silent existence, waiting patiently for the universe to reveal more of its secrets. Beyond the mysterious depths of black holes, the universe continues with countless other wonders that reveal just how creative nature can be. Some of the most beautiful objects in the night sky are not individual stars or planets, but enormous clouds of gas and dust that float peacefully between them. These are known as nebulae. The word itself comes from an ancient word meaning cloud, and that description feels almost perfect. Nebulae are like enormous cosmic clouds drifting through space, sometimes glowing brightly, sometimes hiding in darkness, and often becoming the places where new stars begin their lives. Imagine floating silently through the universe and approaching one of these giant clouds. There would be no wind, no sound, no feeling of movement, only an endless landscape of glowing colors, delicate structures, and ancient materials spread across distances so large that even light needs years to cross them. A nebula may appear gentle and peaceful, but inside these clouds, incredible processes are constantly taking place. Some regions contain cold collections of hydrogen gas where gravity slowly gathers material together. Over millions of years, these areas can collapse and create the conditions needed for new stars to ignite. In this way, nebulae are often called stellar nurseries. They're the places where the universe creates new generations of stars. The process begins quietly. A small region inside a cloud becomes slightly denser than its surroundings. Because it contains more material, its gravity becomes a little stronger. That stronger gravity attracts more gas. More gas creates more gravity. Slowly, patiently, a tiny gathering becomes a massive structure. The collapsing cloud begins to spin. As it contracts, the center becomes hotter and hotter. Eventually, temperatures become high enough for nuclear fusion to begin. A new star awakens. For a moment, the universe creates another source of light. This process is happening throughout galaxies right now. Even as you listen to this story, somewhere far away, clouds of gas are giving birth to stars that no human has ever seen. One of the most famous examples is the Orion Nebula, a vast region of gas located within our own galaxy. Even through a small telescope, it reveals itself as a glowing cloud in the night sky. But modern instruments show something far more extraordinary. A complex landscape filled with newborn stars, swirling gas, and intricate structures shaped by gravity and radiation. The Orion Nebula is not just a beautiful object. It is a place where the future is being created. Inside it, stars are forming that may one day shine for billions of years. Other nebulae tell different stories. Some are created when stars reach the end of their lives. When a star like our Sun eventually runs out of fuel, it will not explode violently like the largest stars. Instead, it will slowly release its outer layers into space, creating a glowing shell of gas called a planetary nebula. The name can be confusing because these objects have nothing to do with planets. Early astronomers gave them this name because some appeared round and planet-like through small telescopes. Today, astrophysicists know they are actually the beautiful final memories of dying stars. At the center of a planetary nebula remains the hot core of the former star, slowly cooling over time. Around it floats a delicate cloud of material that once belonged to the star itself. It is a peaceful ending. A star spends billions of years shining, creating elements in its core, and eventually returns some of its material back to space. That material may later become part of new stars, planets, and perhaps even future life. The universe is constantly recycling itself. Stars are born from ancient material. Stars return material to space. New worlds form from the remains of previous generations. Nothing truly disappears. It simply changes form. Some nebulae are created in much more dramatic ways. When a massive star ends its life in a supernova explosion, the energy can tear the star apart, sending waves of gas racing outward into space. The remains become supernova remnants, beautiful expanding clouds carrying elements forged deep inside the star. The famous Crab Nebula is one example. It is the aftermath of a stellar explosion observed by humans nearly 1,000 years ago. Ancient astronomers recorded a bright object appearing in the sky, visible even during the daytime for a short period. Today, telescopes reveal the glowing remains of that event, still expanding outward after all these centuries. Inside the Crab Nebula lies a rapidly spinning neutron star, the incredibly dense leftover core of the original star. Neutron stars are among the strangest objects known. A single teaspoon of neutron star material would weigh billions of tons on Earth. They are created when gravity compresses a massive star's core so intensely that protons and electrons combine to form neutrons. The result is a city-sized object containing more mass than the Sun. Some neutron stars rotate incredibly quickly, sending beams of radiation through space like cosmic lighthouses. These objects are called pulsars. Every time the beam points toward Earth, astronomers detect a regular pulse of energy. Like a lighthouse flashing across a dark ocean, a pulsar sends signals through space with astonishing precision. Some pulsars are so accurate that scientists compare their timing to the best clocks ever created. The universe can create objects of incredible violence and incredible elegance at the same time. A dying star can create a supernova explosion powerful enough to be seen across galaxies. Yet from that destruction comes creation. The elements scattered by these explosions become the ingredients for future stars and planets. The oxygen you breathe, the carbon in your body, the silicon in rocks beneath your feet, the metals used in technology around you. All of these were formed through cosmic history. The atoms around us are ancient travelers. They have moved through stars, clouds, planets, oceans, and living creatures across billions of years. When we study nebulae, we're not only looking at distant objects, we're looking at the places where the universe builds its future. They are reminders that creation does not always happen quickly. Sometimes the most beautiful transformations require patience. A star may take millions of years to form. A galaxy may take billions of years to evolve. A universe may take nearly 14 billion years to create a moment where someone can lie comfortably at night and wonder about its story. And still, the universe continues changing. Stars are being born. Stars are dying. Galaxies are moving. Space itself is expanding. The cosmic story never truly stops. And hidden throughout this enormous universe is something even stranger. A mysterious substance that does not shine, does not absorb light, and cannot be directly seen, yet appears to hold galaxies together. It is called dark matter, and understanding it may reveal one of the greatest secrets of astrophysics. Dark matter is one of the greatest mysteries in modern astrophysics. It is something that appears to be everywhere throughout the universe, quietly shaping the structure of galaxies and influencing the movement of stars, yet it remains completely invisible to our eyes. It does not glow. It does not reflect light. It does not block light in the way ordinary clouds of dust do. And as far as scientists can tell, it does not interact with normal matter in any obvious way. Its presence can be felt, like an invisible hand gently guiding the movements of cosmic objects. Dark matter seems to provide the hidden framework upon which much of the universe is built. The story of dark matter began when astronomers noticed something unusual. When scientists studied galaxies, they expected stars farther from the center to move more slowly. Much like planets farther from the sun move more slowly in our solar system. But observations revealed something surprising. Stars near the edges of galaxies were moving much faster than expected. According to the amount of visible material scientists could see, those outer stars should have escaped into space. The galaxies should not have been able to hold themselves together. Something unseen appeared to be providing additional gravity. Something invisible was keeping these enormous collections of stars from flying apart. That mysterious something became known as dark matter. The name itself is simple. Dark means we cannot see it. Matter means it appears to have mass and gravity. But beyond those clues, scientists still do not know exactly what dark matter is made of. This mystery is one of the most fascinating examples of how science works. Sometimes discovery does not begin with seeing something. Sometimes it begins with noticing that something is missing. Imagine looking at a beautiful painting and realizing the colors move in a way that suggests another invisible layer exists underneath. You cannot see the hidden layer directly, but its influence changes the entire picture. That is how astronomers experience dark matter. They cannot photograph it. They cannot collect a sample. They cannot place it inside a laboratory container. Instead, they study the way it shapes the universe around it. One of the most important clues comes from the way galaxies rotate. A galaxy is not a solid object spinning like a wheel. It is a huge collection of stars, gas, and dust all moving through space under the influence of gravity. When scientists measure these motions, they find that galaxies behave as if they contain much more mass than we can observe. The invisible material seems to surround galaxies in enormous halos, extending far beyond the regions where stars are visible. In fact, the dark matter halo around a galaxy may be many times larger than the galaxy's glowing disk. Our Milky Way itself is believed to be surrounded by a vast cloud of dark matter. The stars we see represent only a small portion of the total mass that influences our galaxy's behavior. This idea changes the way we imagine the universe. When we look at the night sky and see thousands of stars, we are seeing only the bright surface of a much larger hidden structure. The universe has a visible side, and it has a silent, invisible side. Together, they create the cosmic landscape we observe today. Dark matter also appears to play a major role in the formation of galaxies. After the early universe cooled, tiny variations in the distribution of matter began growing through gravity. Regions with slightly more dark matter attracted additional material, creating invisible foundations where ordinary matter could later gather. Over billions of years, these regions became the homes of galaxies. In a way, dark matter acted like the skeleton of the universe. The stars, planets, and galaxies we see formed around structures that were already there. Without dark matter, the universe might look completely different. Galaxies may not have formed in the same way. Large cosmic structures may never have developed. The universe could have remained a much smoother and quieter place. This invisible substance may have been one of the essential ingredients that allowed the magnificent cosmic web to emerge. When astronomers map the distribution of galaxies across enormous distances, they see patterns resembling a vast network of threads. Galaxies gather along these invisible pathways, forming clusters and filaments separated by enormous empty regions. Dark matter appears to trace these same patterns. It is as if an invisible architecture exists throughout space, quietly organizing the arrangement of galaxies. The mystery becomes even deeper because dark matter does not seem to be made of the same particles that create everything familiar around us. The atoms that form Earth, the Sun, and our bodies are made of ordinary matter. Protons, neutrons, electrons. But dark matter appears to be something entirely different. Scientists have proposed many possibilities. Perhaps it is made of unknown particles that barely interact with normal matter. Perhaps it consists of extremely small particles that pass through Earth constantly without leaving noticeable traces. Perhaps it is connected to physics we have not yet discovered. Many experiments around the world are searching for these hidden particles. Deep underground laboratories are used because Earth's surface is constantly bombarded by radiation and particles from space. By placing detectors far below the ground, scientists reduce interference and create quiet environments where rare interactions might be discovered. So far, dark matter remains hidden, but the search continues. Every unsuccessful experiment still teaches scientists something important. It narrows the possibilities. It removes ideas that do not match reality. And slowly, step by step, humanity moves closer to understanding this invisible part of the universe. Dark matter also creates one of the most beautiful examples of gravity acting as a cosmic lens. Mass bends the path of light. This effect, called gravitational lensing, was predicted by Albert Einstein's theory of relativity. When light from a distant galaxy passes near a massive object, the gravity of that object can curve the light's path, making the background galaxy appear distorted or magnified. By studying these distortions, astronomers can measure where hidden mass exists. Even though dark matter cannot be seen directly, its gravity leaves fingerprints written across the universe. These fingerprints allow scientists to create maps of invisible structures spanning millions of light years. It is a remarkable achievement. Humanity has learned to study something that cannot be photographed by observing how it influences everything around it. Perhaps one day, scientists will discover the true nature of dark matter. Maybe future experiments will reveal new particles. Maybe a completely new understanding of physics will emerge. Or perhaps the answer will surprise everyone and change our view of reality once again. That has happened many times before. The universe has repeatedly shown humanity that nature is far stranger and more creative than imagination alone can predict. Dark matter reminds us to remain curious. It teaches us that what we see is not always the complete story. The universe contains hidden chapters, invisible pages, and quiet mysteries waiting patiently to be discovered. And as we continue exploring the unseen structures of space, another, even more mysterious discovery appears. Something that is not pulling matter together, but pushing the entire universe apart. A force that seems to be increasing with time. A force that may determine the ultimate fate of everything that exists. It is known as dark energy. Dark energy is perhaps one of the most surprising discoveries in the entire history of astrophysics. For a long time, scientists believed they understood the basic story of the expanding universe. They knew that space had been growing since the beginning of the cosmos, and they expected that gravity would slowly slow this expansion down over time. After all, gravity pulls things together. Gravity gathers stars into galaxies. Gravity keeps planets orbiting stars. Gravity brings clouds of gas together to create new worlds. So it seemed natural to assume that gravity would gradually reduce the speed at which the universe expands. But the universe had a surprise waiting. A discovery in the late 20th century changed our understanding of everything. When astronomers studied distant exploding stars called supernovae, they found something unexpected. The expansion of the universe was not slowing down. It was speeding up. Something was causing space itself to expand faster and faster. Scientists gave this mysterious influence a name: dark energy, like dark matter. The name does not mean darkness in the usual sense. It simply describes something that cannot be directly seen. Dark energy does not shine, reflect, or create visible signals. Instead, scientists discover it through its effects on the universe. It is an invisible influence written into the movement of galaxies. To understand why this discovery was so surprising, imagine the universe as a giant stretchable fabric. In the early universe, this fabric began expanding. Scientists expected gravity from all the galaxies and matter within it to slowly pull the fabric back, reducing the expansion. But instead, the opposite appears to be happening. The fabric continues stretching, and the stretching is accelerating. The reason behind this acceleration remains one of the greatest mysteries in science. Dark energy may be a property of space itself. Everywhere space exists, this energy may exist with it. Even completely empty regions between galaxies may contain this mysterious energy, quietly influencing the future of the cosmos. This idea connects to something called vacuum energy. According to quantum physics, empty space is not truly empty. On the smallest scales imaginable, tiny fluctuations may constantly occur, with particles appearing and disappearing in ways that seem almost impossible from an everyday perspective. The emptiness between stars may actually contain a hidden activity that we are only beginning to understand. However, when scientists attempt to calculate the amount of energy that empty space should contain, the results create one of the biggest puzzles in physics. The predictions and observations differ enormously. The difference is so extreme that it has been called one of the greatest unsolved problems in modern science. Somewhere between mathematics and reality, something remains hidden, and that hidden piece may hold the key to understanding the universe itself. Dark energy is difficult to imagine because it does not behave like familiar things. A star pulse, a planet pulse, a black hole pulse. Dark energy appears to have the opposite effect on the largest scales, causing the expansion of space to accelerate. Yet it is not a force pushing galaxies through space like a wind pushing ships across an ocean. Instead, it appears connected to the expansion of space itself. Galaxies are not necessarily racing away because they are moving through a fixed universe. They are being carried apart as the space between them grows. This subtle difference is one of the most beautiful concepts in astrophysics. The universe is not simply a stage where cosmic events happen. The stage itself is changing. Space is dynamic. Space evolves. Space has a history. And perhaps space has a future that we are only beginning to understand. Current observations suggest that dark energy makes up the largest portion of the universe. The visible matter that creates stars, planets, and everything familiar represents only a small fraction. Dark matter contributes another significant portion, but dark energy appears to dominate the cosmic budget. This means that most of the universe is made of things we cannot directly see. The stars shining above us are only a small visible window into a much larger reality. That realization is both humbling and inspiring. Humanity has spent thousands of years studying the heavens, and yet the majority of the universe remains mysterious. We are not surrounded by emptiness. We are surrounded by unanswered questions. The influence of dark energy becomes more noticeable when we look at extremely distant galaxies. Light from these galaxies has traveled across space for billions of years, carrying information from an earlier universe. By comparing their distances and motions, astronomers can study how expansion has changed throughout cosmic history. These observations reveal a universe that has not expanded at a constant rate. Instead, different eras of cosmic history have been shaped by different influences. At first, gravity played a stronger role. Matter gathered together. Galaxies formed. Stars were born. But as the universe grew larger and more spread out, dark energy became increasingly dominant. The empty spaces between galaxies became enormous. And as space expanded, dark energy's influence became stronger. The future of the universe may depend on this mysterious component. If dark energy continues behaving as scientists currently observe, the universe may continue expanding forever. Galaxies outside our local group may eventually move so far away that their light can no longer reach us. Future civilizations, if they exist, might see a much emptier sky than we see today. Many galaxies visible to us now could slowly disappear beyond an invisible cosmic horizon. The universe may become colder, darker, and more isolated over unimaginable periods of time. This possible future is sometimes called the heat death of the universe. Not because the universe becomes hot, but because energy becomes so spread out that nothing remains capable of creating significant change. Stars eventually burn their fuel. Galaxies grow quiet. Black holes slowly lose energy over incredibly long periods. The cosmos approaches a state of maximum calm. Yet astrophysics also reminds us that the future is not completely understood. Dark energy remains mysterious. Perhaps our current understanding is incomplete. Perhaps new discoveries will reveal a different story. Throughout history, scientific revolutions have happened when humanity discovered that nature was more complex than expected. The Earth was not the center of the universe. Time was not absolute. Space was not fixed. Atoms were not the smallest things. Each discovery expanded our understanding and opened new questions. Dark energy may represent another doorway into a deeper reality. It may lead us toward new physics, new theories, and new ways of understanding existence itself. There's something beautifully peaceful about this mystery. The universe is billions of years old. It is vast beyond imagination. And yet, hidden within its enormous scale, there are still secrets waiting for curious minds to uncover. Every galaxy drifting through space. Every star glowing in the darkness. Every photon traveling across billions of years. Every question we ask, all of it is part of the same cosmic journey. And as we continue traveling through astrophysics, we now turn toward one of the most important ideas connecting everything we have explored so far. The strange relationship between space, time, gravity, and the very structure of reality itself. The universe is not simply a collection of objects floating inside an empty container. For a long time, humans imagined space as a vast, motionless stage where stars, planets, and galaxies moved around like actors in a giant cosmic theater. Space was thought to be separate from everything happening within it. But the discoveries of modern astrophysics revealed something far more extraordinary. Space itself is part of the story. Time itself is part of the story. Together, they create something called spacetime. This idea transformed our understanding of reality. Before the 20th century, many scientists believed that time flowed the same way everywhere in the universe. A second on Earth was thought to be the same as a second anywhere else. But then a young physicist named Albert Einstein introduced ideas that changed the way humanity viewed the cosmos forever. His theory of relativity revealed that space and time are connected, forming one combined fabric that can bend, stretch, and change depending on motion and gravity. This sounds strange because our everyday experience tells us something different. A clock seems simple. A minute seems like a minute. A meter seems like a meter. But the universe does not always follow our everyday intuition. Reality is much more flexible than it appears. One of the most beautiful examples is time dilation. According to relativity, time does not pass at exactly the same speed everywhere. A person moving extremely fast experiences time slightly differently from someone moving more slowly. The difference is tiny at ordinary speeds, but becomes significant when objects approach the speed of light. Imagine two twins. One remains safely on Earth. The other travels through space in a spacecraft, moving incredibly close to the speed of light. When the traveling twin returns, they would have aged less than their sibling on Earth. The traveler would have experienced only a short journey, while much more time would have passed for those who stay behind. This is not science fiction. It is a real effect measured through extremely precise experiments. The universe itself allows different people to experience time differently depending on their movement. Gravity also affects time. The stronger the gravitational field, the slower time passes. This means a clock closer to a massive object ticks slightly slower than a clock farther away. On Earth, the difference is extremely small, but scientists can measure it using incredibly accurate clocks. Near a black hole, however, the effect becomes dramatic. The intense gravity creates such a strong distortion of space-time that time itself behaves in ways that seem almost impossible. A person near a black hole would experience time passing normally from their own perspective, but someone far away would see their clock moving much more slowly. This strange relationship between gravity and time reveals something profound. Gravity is not simply a mysterious pulling force. It is a result of the shape of space-time itself. Massive objects tell space-time how to curve, and curved space-time tells objects how to move. A planet does not orbit the sun because an invisible rope pulls it around. Instead, the sun creates a curve in space-time, and Earth follows that curved path. This description is difficult to visualize, but it represents one of humanity's deepest discoveries about nature. The universe is not built from separate pieces. Everything is connected. Space, time, matter, energy, all influence one another. One of the greatest confirmations of Einstein's ideas came from the discovery of gravitational waves. These are tiny ripples in space-time created by accelerating massive objects. When two black holes orbit each other and eventually merge, they create waves that travel outward across the universe. These ripples are unbelievably small by the time they reach Earth. The stretching and squeezing they create is far smaller than the width of an atomic nucleus. Yet in 2015, scientists detected them for the first time using incredibly sensitive instruments. Humanity had discovered a completely new way to observe the universe. Before gravitational waves, almost everything we learned about space came from light. Radio waves, visible light, X-rays, gamma rays. But gravitational waves opened another window. They allowed scientists to study events that may produce little or no light at all. The universe had gained a new voice. These waves also provide a direct connection to some of the most powerful events in existence. When two black holes merge, the final moments before their collision create enormous distortions in space-time. The energy released can briefly surpass the combined light output of all the stars in the observable universe. Yet instead of shining brightly, that energy travels outward as invisible waves moving through the fabric of reality. There is something beautifully peaceful about this idea. The universe is constantly moving. Stars are exploding. Galaxies are merging. Black holes are dancing. And through it all, space-time carries the echoes of these events across billions of years. Every discovery in relativity also reminds us how limited human intuition can be. Our brains evolved to understand walking, climbing, weather, and daily life on Earth. They were not naturally designed to imagine curved space-time, four-dimensional geometry, or objects moving close to the speed of light. Yet through mathematics, observation, and curiosity, humans have learned to understand parts of a reality far beyond ordinary experience. This is one of the most inspiring aspects of astrophysics. The universe is enormous, but the human mind can still reach toward it. A telescope can collect ancient light from distant galaxies. A mathematical equation can describe the behavior of stars. A scientific idea can travel across generations. And a person lying quietly at night can imagine worlds billions of light years away. The connection between space and time also changes how we think about distance. When we look at distant galaxies, we're not only seeing far away, we are seeing the past. A galaxy located 10 billion light years away appears as it looked 10 billion years ago, because that is how long its light needed to reach us. Every telescope pointed toward the universe becomes a window through time. The night sky is filled with ancient memories. Some stars visible tonight may have already changed or disappeared, but their light continues traveling through space, allowing us to see a version of them from the past. The universe preserves its history in motion. And perhaps one of the most fascinating questions created by relativity is whether humans could ever travel through space-time in unusual ways. Could there be shortcuts across the universe? Could wormholes connect distant locations? Could time travel ever be possible? These ideas come from serious mathematical discussions in physics. Although no evidence currently shows that humans can create or use such pathways, the universe allows imagination to explore possibilities, but science carefully separates beautiful ideas from confirmed reality. That balance between curiosity and evidence is what makes astrophysics so powerful. It allows us to dream while keeping our feet connected to truth. As we continue our journey through the universe, we now move toward another breathtaking mystery. A story written not only in stars and galaxies, but in the very first moments after the universe began. A faint glow that still travels through space today. A quiet signal from the childhood of the cosmos. The ancient light, known as the cosmic microwave background. Long before galaxies filled the universe with their brilliant spirals, before stars illuminated the darkness, and before planets formed around distant suns, the universe was much younger, hotter, and simpler. It was a place unlike anything we could experience today. A universe filled with energy. A universe filled with particles. A universe still discovering what it would eventually become. And hidden within the darkness of space today is a faint message from that ancient era. A quiet glow that has traveled for nearly the entire age of the universe. This ancient signal is called the cosmic microwave background. It is one of the greatest discoveries in astrophysics because it allows scientists to look back toward the earliest moments after the universe began. It is like finding a photograph of the universe as a newborn. Not a photograph taken with a camera, but a photograph created by ancient light. To understand this remarkable discovery, we must return to a time when the universe was only a few 100,000 years old. At that time, the cosmos was still incredibly hot. The temperature was thousands of degrees. Atoms could not exist in the peaceful form we know today because the energy around them was too intense. Electrons and atomic nuclei moved freely through space, creating a thick fog that trapped light. Imagine trying to see through a dense cloud. Light exists, but it cannot travel very far before interacting with the particles around it. The early universe was similar. It was filled with light, but that light was trapped. Then something important happened. As the universe expanded, it continued cooling. Eventually, the temperature became low enough for electrons to combine with atomic nuclei and form the first stable atoms. This moment is known as recombination. It was not an explosion. It was not a dramatic event that anyone could have witnessed. It was simply a quiet transition, a moment when the universe became transparent. For the first time, light could travel freely across space. The photons released during this period began an incredible journey. They traveled through an expanding universe. They passed through billions of years of cosmic history. They moved through changing galaxies, growing structures, and the formation of stars and planets. And today, some of those ancient photons are still traveling. They arrive from every direction in the sky. They surround Earth. They're the oldest light humans can directly observe. The cosmic microwave background. At first, scientists did not know it existed. Its discovery happened almost accidentally. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive antenna designed for communication experiments. They noticed a strange background signal coming from every direction. No matter where they pointed their instrument, the signal remained. They checked their equipment. They searched for possible sources. They even investigated whether something inside the antenna was causing the problem. But the mysterious signal remained. Eventually, they realized they had discovered something extraordinary. They had found the leftover radiation from the beginning of the universe. A message that had been traveling for billions of years. This discovery provided powerful evidence supporting the idea that the universe had a hot, dense beginning. The cosmic microwave background became one of the most important pieces of evidence in modern cosmology. Today, advanced space telescopes have mapped this ancient light with incredible detail. These maps reveal tiny temperature differences across the early universe. At first glance, these differences seem incredibly small, but they're among the most important clues we have about how galaxies formed. The slight variations in the cosmic microwave background represented tiny differences in density. Some areas contained slightly more matter. Others contained slightly less. Over billions of years, gravity amplified these small differences. The slightly denser regions attracted more material. Those regions eventually became the foundations for galaxies, clusters of galaxies, and the enormous structures we observe today. In a beautiful way, the galaxies shining across the night sky began as tiny patterns written into the universe's earliest light. The cosmic microwave background also reveals information about the universe's age, composition, and geometry. By studying this ancient glow, scientists can estimate how old the universe is and understand how different components contribute to its evolution. It tells us that the universe is approximately 13.8 billion years old. It reveals the presence of ordinary matter. It provides clues about dark matter, and it helps scientists understand the influence of dark energy. A faint whisper from the beginning of time contains information about the entire cosmic story. This is one of the most beautiful ideas in astrophysics. The universe remembers, not through words, not through written records, but through light. Every part of the cosmos carries traces of its history. The positions of galaxies, the movements of stars, the radiation traveling through space. All of these are clues left behind by the universe itself. The cosmic microwave background is especially fascinating because it comes from a time before stars existed. When we look at modern galaxies, we see the universe after billions of years of evolution. But when we observe this ancient radiation, we see the universe before complexity, before planets, before oceans, before life, before anyone was here to wonder about it. It is a glimpse into the universe's earliest childhood. Scientists continue studying this ancient light because many questions remain unanswered. What happened during the earliest moments before this radiation was released? How did the first tiny variations form? What exactly caused the rapid expansion of the universe's earliest moments? Could there be information hidden within the patterns we have not yet understood? Each discovery opens another door, and behind every door is another mystery. Perhaps that is why astrophysics is so captivating. The universe gives us answers, but those answers reveal even deeper questions. It is a never-ending journey of curiosity. The cosmic microwave background also carries another beautiful message. The universe we see today was not always here. The stars were not always shining. The galaxies were not always glowing. Everything familiar emerged slowly through time. The universe grew. It changed. It evolved. And eventually, after billions of years, it created a place where conscious beings could look back and ask where everything came from. The atoms in your body were created in stars. The elements around you were formed through cosmic history. And the light entering telescopes today began traveling long before Earth existed. You are connected to a universe much older than yourself. A universe that has spent billions of years becoming what it is now. And still, the journey continues. Because beyond the ancient glow of the cosmic microwave background lies another fascinating question. How did the first stars awaken? How did the first galaxies transform a dark universe into the brilliant cosmos we see today? To answer that, we must travel back into the earliest chapters of cosmic evolution and explore the incredible era when the first lights appeared. Before the universe became filled with the brilliant glow of countless stars, there was a long and quiet period known as the Cosmic Dark Ages. It was not dark because anything was wrong. It was dark because the universe was waiting. The ingredients for everything we know today were already present. Hydrogen atoms filled the expanding cosmos. Gravity gently shaped the distribution of matter. The first structures were beginning to form, but there were no stars yet. No galaxies shining through the darkness. No sources of light illuminating the enormous spaces between galaxies. The universe was young, silent, and peaceful. Imagine drifting through this ancient cosmos. There would be no familiar constellations, no glowing Milky Way stretching across the sky, no distant galaxies appearing as tiny islands of light. Only an endless ocean of hydrogen, slowly changing over millions of years. Yet hidden inside this darkness was a remarkable transformation waiting to happen. Gravity was preparing the universe for its first sunrise. The first stars were unlike the stars we see today. They were created from nearly pure hydrogen and helium, the simplest elements that emerged after the beginning of the universe. There were almost no heavier elements available. No carbon, no oxygen, no iron, no materials that would later create rocky planets and living organisms. The universe had to build those ingredients first. The first stars were enormous compared with many stars born later, because the early universe contained only simple elements. Massive clouds of gas could collapse into extremely large stars. Some of these ancient stars may have been hundreds of times more massive than our sun. They burned intensely, they lived quickly, and they ended their lives dramatically. A star that survives for billions of years like our sun was not typical among the earliest generation. Many of the first stars existed for only a few million years before reaching the end of their lives. But during that short existence, they changed the universe forever. Inside their powerful cores, nuclear fusion created heavier elements. Hydrogen became helium. Helium became carbon. Carbon and other elements formed through increasingly complex reactions. These stars became the first cosmic factories. They transformed a simple universe into a chemically rich one. When many of these giant stars eventually exploded as supernovae, they scattered these newly created elements throughout space. The universe became enriched. The ingredients for future stars, planets, and life began spreading across galaxies. In a profound way, the first stars prepared the universe for everything that came after them. Their light also changed the environment around them. The young universe was filled with neutral hydrogen atoms that absorbed certain types of radiation. But the intense ultraviolet light from the first stars began breaking these atoms apart, allowing light to travel farther. This period is known as the era of reionization. It was a cosmic transformation on an enormous scale. The first stars were not just sources of light. They were architects of change. They reshaped the universe around them. Over time, groups of early stars gathered together. Gravity pulled them into larger structures. These became the first galaxies. At first, these galaxies were much smaller and more chaotic than the majestic spirals and elliptical galaxies we observe today. They were collections of young stars, gas, and dark matter, slowly growing through collisions and mergers. The universe was beginning to organize itself. Small structures became larger structures. Simple beginnings became incredible complexity. This process continues even today. Galaxies are not frozen objects. They are living systems evolving through time. Stars are born. Stasti. Gas moves. Galaxies emerge. New generations replace old ones. The universe is constantly writing new chapters. One of the most fascinating discoveries in modern astrophysics is that looking farther away in space allows us to see farther back in time. Because light requires time to travel, distant galaxies show us what the universe looked like long ago. The earliest galaxies observed by telescopes appear different from those nearby. They are often smaller, more irregular, and filled with active star formation. They represent the universe during its younger years. Modern instruments continue pushing this boundary, searching for some of the earliest galaxies that formed after the first stars. Every ancient galaxy discovered is like finding another page from the universe's childhood. It tells scientists how quickly structures formed, how stars evolved, and how the cosmos changed from a simple beginning into the complex universe we know today. The formation of galaxies is a story of balance. Gravity pulls matter together. Energy from stars pushes material outward. Dark matter provides invisible foundations. Dark energy influences the universe on the largest scales. All of these forces interact across billions of years. The galaxies we see today are the results of countless cosmic conversations between these different influences. Our own galaxy, the Milky Way, carries memories of this long history. Hidden within its stars are clues about previous generations. Some stars contain elements created inside ancient stars that lived and died before the Milky Way fully formed. By studying these stars, astronomers can learn about the early history of our galaxy. It is like reading tree rings in an ancient forest. Each layer contains information about the past. Each star carries a piece of cosmic history. The universe also teaches us something important about patience. Human beings often think in years or decades, but the cosmos operates on scales of millions and billions of years. A galaxy does not form overnight. A star is not created in a moment. A planet does not become a home instantly. The universe builds slowly, step by step, atom by atom, star by star, galaxy by galaxy. And after billions of years of cosmic evolution, one remarkable planet formed around an ordinary star in a quiet region of one galaxy. That planet would eventually develop oceans, forests, and life. It would produce creatures capable of looking upward and wondering about the universe that created them. But before we return to Earth, our journey through astrophysics continues deeper into the universe. Because scattered across the cosmos are enormous explosions that briefly become brighter than entire galaxies. Events that create many of the elements around us. Events that mark the dramatic endings of some of the universe's greatest stars. These are supernovae, the spectacular deaths that help create new beginnings. A star's life is a story written across millions or billions of years. It begins quietly inside a cloud of gas and dust. It grows brighter as gravity gathers material together. It shines steadily as nuclear fusion balances the enormous weight pressing inward. And eventually, depending on its size, it reaches a final chapter. For some stars, the ending is gentle. For others, the ending is one of the most powerful events in the universe. A supernova. The word itself sounds dramatic, and the reality is equally extraordinary. A supernova is not simply a star disappearing. It is a cosmic transformation, a moment when a star releases unimaginable energy, scattering elements across space and creating conditions for future generations of stars, planets, and perhaps life. To understand a supernova, we must first understand the delicate balance that allows a star to exist. A star is constantly experiencing a struggle between two forces. Gravity pulls everything inward. The energy produced by nuclear fusion pushes outward. For most of a star's life, these forces remain beautifully balanced. The star does not collapse. The star does not explode. It simply shines. Inside the core of a massive star, temperatures and pressures become so extreme that lighter elements combine to create heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon can become oxygen and other elements. Eventually, some massive stars create elements as heavy as iron. But iron represents a turning point. Unlike earlier fusion reactions, creating elements heavier than iron does not release energy. The star reaches a point where its core can no longer produce enough energy to fight gravity. The balance breaks. Gravity begins winning. The core collapses inward with incredible speed. In just seconds, a region larger than Earth can compress into an object only a few kilometers across. The collapse creates unimaginable conditions. The atoms themselves are crushed. Electrons are forced into protons. Together, they create neutrons. The result is one of the strangest objects in existence, a neutron star. The collapsing core suddenly becomes extremely resistant to further compression, creating a powerful rebound. That rebound sends shock waves outward through the star. The outer layers are blasted into space. The star explodes. For a brief moment, the supernova can shine brighter than billions of ordinary stars combined. A single dying star can become visible across an entire galaxy. The explosion is both an ending and a beginning. The star that existed for millions of years is gone, but from its remains, new possibilities emerge. Supernovae create and spread many of the heavier elements needed for planets and life. Before these explosions, the universe contained mostly hydrogen and helium. But through generations of stars living and dying, space became filled with carbon, oxygen, nitrogen, silicon, and many other elements. The universe became capable of creating rocky planets, oceans, and living organisms. In a very real sense, supernovae helped make worlds like Earth possible. The iron in your blood was once created inside an ancient star. The calcium in your bones was forged through cosmic processes billions of years ago. The elements that form mountains, oceans, and living cells all carry the history of stellar evolution. The universe built the ingredients for life inside stars. Then it scattered those ingredients across space. Supernovae are also incredibly important tools for astrophysicists. Because their brightness can be measured, they help scientists understand distances throughout the universe. Some types of supernovae have predictable brightness, allowing astronomers to use them as cosmic markers. By comparing how bright these explosions appear with how bright they should be, scientists can estimate how far away their galaxies are. These observations helped reveal one of the greatest discoveries in modern cosmology, the accelerating expansion of the universe. A dying star helped humanity understand the fate of the entire cosmos. That is one of the beautiful connections in astrophysics. The smallest details can reveal the largest truths. A single explosion in a distant galaxy can teach us about the structure of the universe itself. Supernovae also create breathtaking remnants. After the explosion, clouds of gas continue expanding outward into space. These remnants can last for thousands or even millions of years. They become glowing structures filled with complex shapes and colors. Inside them, newly created elements continue their journey. Some material may eventually become part of new stars. Some may become planets. Some may become part of living organisms. The universe constantly recycles its creations. One generation of stars creates the ingredients needed for another. The death of one star becomes the beginning of countless future stories. There are different kinds of supernovae, each revealing different astrophysical processes. Some occur when massive stars collapse under their own gravity. Others happen when a white dwarf, the leftover core of a smaller star, accumulates too much material from companion star and becomes unstable. Although the causes differ, the result is always a spectacular release of energy. These explosions allow scientists to study extreme physics that cannot be recreated easily on Earth. They reveal how matter behaves under incredible pressure and temperature. They show how elements are created. They provide clues about how galaxies evolve. And they remind us that the universe is constantly changing. A peaceful night sky can sometimes feel eternal. The stars appear fixed and unchanging. But behind that calm appearance is a universe full of motion. Stars are born. Stars evolve. Stars disappear. Galaxies transform. The cosmos is not a painting hanging still on a wall. It is an ongoing story. A story written in light. A story carried through time. One of the most fascinating examples of this cosmic change comes from stars much smaller than the giants that create supernovae. Stars like our own sun, they follow a different path. They do not end with a massive explosion. Instead, they slowly transform into beautiful remnants called white dwarfs. These small, incredibly dense objects represent another peaceful ending in the long journey of stars. And studying them helps astrophysicists understand not only the future of stars, but also the distant future of the universe itself. Not every star ends its life with a spectacular explosion. Some stars choose a quieter path. They do not collapse into black holes. They do not create enormous supernovae. Instead, after billions of years of shining peacefully, they slowly release their outer layers and leave behind a small, incredibly dense core known as a white dwarf. Our own sun will follow this path one day, but that moment is unimaginably far into the future. The sun is currently about 4.6 billion years old, and it still has billions of years of life remaining. Every second, deep inside its core, it transforms hydrogen into helium through nuclear fusion, releasing the energy that warms Earth and allows life to exist. But even stars have limited fuel. Eventually, the hydrogen in the sun's core will begin running low. The delicate balance that has kept the sun stable for billions of years will slowly change. Gravity will begin compressing the core more strongly. As the core becomes smaller and hotter, the outer layers of the sun will expand. The sun will become a red giant. For a short period in cosmic history, our familiar star will become enormous, extending far beyond its current size. Its surface will cool, giving it a reddish appearance. From distant worlds, it would appear completely transformed. The sun will no longer look like the calm yellow star we see today. It will become a giant, glowing sphere near the end of its life. Eventually, the outer layers of the sun will drift away into space. These layers will create a beautiful cloud of gas known as a planetary nebula. Again, despite the name, there are no planets involved. The term came from early astronomers who observed these round, glowing shapes through small telescopes and thought they resembled planets. Today, we know these structures are the final memories of dying stars. At the center of this beautiful cloud will remain the sun's core, a white dwarf, a tiny object compared with the original star, yet incredibly massive. A white dwarf can contain a large fraction of the sun's mass packed into a volume similar to Earth. This means its material is extraordinarily dense. A small amount of white dwarf material would weigh an astonishing amount on Earth. The reason white dwarfs can exist in this unusual state is due to a quantum mechanical effect called electron degeneracy pressure. This is one of the places where astrophysics reveals the strange behavior of matter at extreme conditions. Ordinary experiences tell us that if something becomes too heavy, it collapses. But the laws of quantum physics create limits on how closely certain particles can be compressed. Electrons resist being forced into identical states. This resistance helps support the white dwarf against gravity. The star is no longer powered by nuclear fusion. It simply slowly cools over immense periods of time. A white dwarf is like a cosmic ember, a leftover piece of a once brilliant star, quietly fading through the darkness. The universe contains many white dwarfs. Some are located within our own galaxy, silently traveling through space after their former stars completed their journeys. They remind astrophysicists that not every ending needs to be violent. Sometimes transformation happens slowly. Sometimes the universe changes through gentle processes. White dwarfs also provide important clues about the history of stars. By studying their temperatures, compositions, and movements, scientists can learn how old stellar populations are and how galaxies have evolved over time. Because white dwarfs cool in predictable ways, they can act like cosmic clocks. A very cool white dwarf is usually older than a very hot one. By measuring their temperatures, astronomers can estimate the ages of groups of stars. These tiny remnants preserve memories of ancient stellar generations. Another fascinating possibility exists when a white dwarf has a companion star nearby. Sometimes a white dwarf can pull material away from its companion. The stolen gas collects around the white dwarf, creating a swirling disk of material. As more matter accumulates, the white dwarf can become unstable. In some cases, this leads to a powerful explosion called a type Ia supernova. This connection between quiet stellar remnants and enormous explosions shows how interconnected the universe truly is. A star that appears finished may still play an important role in cosmic evolution. The story of white dwarfs also connects to the distant future of the universe. Imagine a time when most stars have burned through their fuel. New stars become rarer. Galaxies become quieter. The universe grows older. The remaining stars slowly fade. In this far future, white dwarfs may become some of the most common stellar objects remaining. Over unimaginable lengths of time, they will continue cooling. Eventually, they may become cold, dark objects sometimes called black dwarfs. However, the universe is not old enough for any black dwarfs to exist yet. The time required for a white dwarf to cool completely is far longer than the current age of the cosmos. Even the universe itself is still young compared with some of the timescales astrophysics describes. This is one of the most fascinating lessons from studying stars. Human lives are measured in decades. Civilizations are measured in thousands of years. Stars are measured in millions or billions. The universe operates on a scale that stretches beyond ordinary imagination. And yet, despite these enormous distances in time and space, the story of stars connects directly to us. The sun provides the energy that supports life. Ancient stars created the elements inside our bodies. The light from distant stars inspires curiosity. The universe is not separate from our existence. We are part of the same process. A white dwarf is a reminder that even after a star's brightest days are over, its story continues. Its material remains. Its influence remains. Its atoms may one day become part of something new. The universe rarely wastes anything. Everything transforms. Everything moves. Everything becomes part of another chapter. And as we continue our journey through astrophysics, we now move towards some of the most extreme objects ever discovered. Places where matter becomes compressed beyond ordinary understanding and where nature creates the strongest magnetic fields known. We enter the strange world of neutron stars and pulsars. Among all the objects created by the universe, few are as extraordinary as neutron stars. They are the remains of massive stars that once burned brightly for millions of years. Stars that created elements inside their cores. Stars that eventually reached the end of their lives and transformed into something completely different. A neutron star is a world of extremes. It contains more mass than the sun. It can spin hundreds of times every second. It can produce magnetic fields trillions of times stronger than Earth's. Yet it is only about the size of a city. This incredible combination of enormous mass and tiny size makes neutron stars some of the densest objects known in the universe. To understand how a neutron star forms, we return to the final moments of a massive star. When such a star can no longer support itself, its core collapses under the force of gravity. The pressure becomes so intense that electrons are pushed into protons. Together, they form neutrons. The star's core transforms into a sphere made mostly of these tiny particles. The result is a neutron star. The collapse is almost impossible to imagine. A star that may have been millions of kilometers wide becomes an object only a few dozen kilometers across. The material inside becomes packed so tightly that a small amount would have an unbelievable weight if brought to Earth. The surface of a neutron star is also unlike anything we know. The gravity is incredibly powerful. If you could stand on its surface, ignoring the fact that it would be impossible, you would experience a gravitational pull billions of times stronger than Earth's. A mountain on a neutron star would not remain a mountain. The immense gravity would flatten almost everything into a smooth surface. The environment would be completely alien. The intense pressure, extreme temperatures, and powerful magnetic fields create conditions that scientists can only study through observations and theories. Inside neutron stars, matter may exist in forms that do not naturally occur anywhere else in the universe. The deeper we explore, the more mysterious these objects become. Some neutron stars rotate incredibly quickly. These are called pulsars. A pulsar acts like a cosmic lighthouse. It sends beams of radiation from its magnetic poles. As the neutron star spins, those beams sweep across space. When one of the beams points toward Earth, telescopes detect a regular pulse of energy. A signal appears, then disappears, then returns again, like a lighthouse flashing across a dark ocean. The discovery of pulsars was one of the most fascinating moments in astronomy. In 1967, astronomer Jocelyn Bell Burnell detected strange repeating signals while studying radio waves from space. At first, the signals were so regular that scientists jokingly considered whether they might come from an intelligent civilization. But the truth was even more fascinating. They were natural signals from a rapidly rotating neutron star. The universe had created its own incredibly precise cosmic clock. Some pulsars rotate dozens of times per second. Others rotate hundreds of times per second. The fastest known pulsars complete hundreds of rotations every second, with their surfaces moving at incredible speeds. Despite this motion, they remain stable because gravity holds their structure together with tremendous strength. Neutron stars also possess some of the strongest magnetic fields in existence. These magnetic fields can accelerate particles to enormous energies, creating powerful radiation that travels across space. Some neutron stars with especially intense magnetic fields are called magnetars. Magnetars are among the most extreme objects known. Their magnetic fields are trillions of times stronger than Earth's. If a magnetar came relatively close to our planet, its magnetic influence could dramatically affect technology and even the structure of atoms. Fortunately, the nearest known magnetars are incredibly far away. The universe often creates powerful objects, but also places them at safe distances. Neutron stars also reveal important information about physics under extreme conditions. On Earth, scientists study matter in laboratories. They can create high temperatures, intense pressures, and powerful magnetic fields. But nature creates environments far beyond anything humans can reproduce. Neutron stars become natural laboratories scattered throughout the galaxy. By studying their behavior, scientists learn about nuclear physics, gravity, and the fundamental structure of matter. Some neutron stars exist in binary systems orbiting another star. These systems can create fascinating interactions. A neutron star may pull material from its companion, causing gas to spiral toward the neutron star's surface. As the material falls, it releases enormous amounts of energy. The result could be powerful bursts of X-rays that reveal the hidden activity of these distant objects. Sometimes two neutron stars themselves can collide. When this happens, The event is among the most energetic occurrences in the universe. The collision creates gravitational waves that travel across space. It also produces heavy elements through a process called neutron capture. Gold, platinum, many rare elements found on Earth may have been created during ancient neutron star mergers. The jewelry humans wear, the metals used in technology, and the materials around us may contain atoms forged in some of the most violent events in cosmic history. Once again, astrophysics connects the smallest pieces of matter to the largest events in the universe. The gold on Earth is not simply a material found beneath our feet. It carries a cosmic history. It may have traveled through space for billions of years before becoming part of our world. Neutron stars also challenge our understanding of what is possible. They show that matter can exist in states far beyond everyday experience. They demonstrate how gravity can reshape entire stars. They reveal that the universe is capable of creating objects that seem almost impossible. Yet these objects are not fantasy. They are real. They are observed. They are part of the universe we inhabit. Every neutron star is a reminder that the cosmos is not only vast. It is also incredibly creative. From simple atoms to giant galaxies, nature explores an enormous range of possibilities. And sometimes, after exploring the lives and deaths of stars, astrophysicists turn their attention to something even larger. Not individual stars, not single galaxies, but the enormous structures formed when thousands of galaxies gather together. The universe contains cities of galaxies connected by gravity across unimaginable distances. These are galaxy clusters, the largest bound structures in the cosmos. Across the vast darkness of a universe, galaxies are not scattered randomly. Although space appears empty when we look between the stars, the cosmos is filled with enormous patterns and structures created by gravity over billions of years. Among the largest of these structures are galaxy clusters. A galaxy cluster is exactly what its name suggests, a massive collection of galaxies held together by gravity. But the true scale of these objects is almost impossible to imagine. A single cluster can contain hundreds or even thousands of galaxies. Each galaxy may contain billions of stars, and many of those stars may have their own planets. When we look at a galaxy cluster, we are not seeing one enormous object. We are seeing a city of cosmic cities, a gathering of countless worlds connected across unimaginable distances. The largest galaxy clusters can span millions of light years. To travel from one side to the other at the speed of light would take longer than the entire history of human civilization. Yet from the perspective of the universe, these structures are part of a much larger pattern. Galaxy clusters are connected through the cosmic web, an enormous network of galaxies, gas, and dark matter stretching throughout the observable universe. This cosmic web resembles a giant structure of invisible threads. Along these threads, galaxies gather together. Between them are enormous empty regions called cosmic voids. These voids are not completely empty, but compared with the crowded regions of galaxies, they contain very little matter. The universe has created a beautiful balance between connection and isolation. Dense regions where galaxies gather. Quiet spaces where almost nothing exists. All shaped by the gentle influence of gravity over billions of years. The formation of galaxy clusters began shortly after the early universe. Tiny differences in the distribution of matter created areas with slightly more density. gravity slowly amplified these differences. More matter gathered, more gravity developed. Eventually, enormous structures began forming. The first galaxies appeared. Then galaxies began merging. Groups became clusters. Clusters became part of even larger cosmic patterns. The universe built complexity slowly, one step at a time. One of the most fascinating aspects of galaxy clusters is that the galaxies themselves are not the majority of the mass. Most of the cluster's mass is believed to come from dark matter. The invisible substance that helps hold galaxies together also helps shape the largest structures in the universe. Without dark matter, galaxy clusters would behave very differently. The galaxies inside them might move apart instead of remaining connected. Again, the universe reveals that what we cannot see may be just as important as what we can. Between the galaxies inside clusters exists something called the intracluster medium. It is a vast ocean of extremely hot gas spread throughout the cluster. This gas can reach temperatures of millions of degrees, although it is incredibly thin compared with Earth's atmosphere. There is enough of it spread across such enormous distances that it contains more ordinary matter than all the stars within the galaxies combined. Because the gas is so hot, it releases powerful X-rays. Special telescopes designed to observe X-ray light allow astronomers to study these invisible oceans between galaxies. These observations reveal how clusters grow, how matter moves, and how energy flows through the universe. Galaxy clusters also provide some of the best opportunities to study gravitational lensing. Because clusters contain enormous amounts of mass, they bend the path of light from objects behind them. A distant galaxy may appear stretched, brightened, or distorted because its light passes through the gravitational field of a foreground cluster. These cosmic lenses act like natural telescopes created by the universe itself. They allow astronomers to observe galaxies that might otherwise be too distant and faint to detect. It is one of the most beautiful examples of nature helping us explore nature. The universe provides the tools needed to understand itself. Some galaxy clusters are calm and ancient. Others are experiencing dramatic interactions. When two clusters move toward each other, their immense gravitational fields begin interacting. The galaxies within them may pass through one another. The hot gas can collide and create enormous shock waves. Dark matter may separate from ordinary matter. These events can reveal important clues about the invisible components of a universe. One famous example is the Bullet Cluster. This system formed after two galaxy clusters collided. The collision created a unique arrangement where scientists could compare the locations of ordinary matter and dark matter. Observations showed that much of the mass was not located where the visible gas was found. This provided strong evidence supporting the existence of dark matter. Galaxy clusters also help scientists understand the expansion of the universe. Because they are so massive and contain so many galaxies, they act as important markers for studying how cosmic structures have evolved over time. By observing clusters at different distances, astronomers can look back through different stages of a universe's history. A nearby cluster shows us the universe more recently. A distant cluster shows us the universe as it appeared billions of years ago. Each cluster becomes a time capsule, a collection of galaxies preserving memories of cosmic evolution. Perhaps the most beautiful thing about galaxy clusters is their scale. On Earth, we often think in terms of cities, continents, and oceans. But the universe creates cities of stars. Structures so enormous that individual galaxies become like neighborhoods within something much greater. And yet, even these enormous clusters are not the largest structures we know. The cosmic web extends farther. Filaments of galaxies stretch across hundreds of millions of light years. Giant superclusters contain multiple galaxy clusters connected through gravity. The universe continues building larger and larger patterns. But even the largest structures eventually lead us back to a deeper question. Where did everything begin? How did a universe filled with galaxies, stars, planets, and life emerge from its earliest moments? To understand the grand story of astrophysics, we must return once more to the beginning, to the first instant of creation, to the moment when space itself began expanding, to the mysterious event that started the journey of everything we know, the birth of the universe. The story of the universe begins with a question that has fascinated humanity for thousands of years. Where did everything come from? Every star in the sky, every galaxy drifting through space, every planet circling a distant sun, every atom that forms the world around us. All of it has a beginning. Astrophysics takes us back to the earliest moments of existence, when the universe was not filled with galaxies or stars, but was instead a hot, dense state of energy and particles. A beginning beyond ordinary imagination. The event that describes this beginning is known as the Big Bang. But the Big Bang was not an explosion happening inside empty space. There was no empty room waiting for something to appear. Space itself was part of the event. Time itself began as part of this unfolding. The universe did not expand into something outside of itself. The universe expanded. Everything that exists today was once contained within an incredibly hot and dense early state. Then, approximately 13.8 billion years ago, the universe began expanding. At the earliest moments, the universe was unimaginably different from what we see today. There were no stars, no galaxies, no planets, no familiar structures, only energy in the simplest forms of matter. The temperatures were beyond anything humans can recreate. Particles moved with incredible energy. The forces that shape the universe today were once combined in ways that scientists are still trying to fully understand. The universe was young. The universe was changing. The universe was beginning its long journey toward complexity. One of the most remarkable ideas in astrophysics is that the entire visible universe came from this extremely simple beginning. The atoms inside your body, the elements inside Earth, the stars shining above you, all of them trace their history back to those first moments. The universe began small in a cosmic sense. Then it grew. As space expanded, temperatures gradually decreased. Cooling allowed new forms of matter to appear. The earliest particles began forming the foundations of atoms. Eventually, the simplest elements emerged. Hydrogen, helium, tiny amounts of other light elements. These became the raw materials for everything that would follow. For hundreds of thousands of years, the universe remained filled with a hot mixture of particles and radiation. Light could not travel freely. The cosmos was like a glowing fog. But as expansion continued, the universe cooled enough for atoms to form. The fog disappeared. Light was released. That ancient light continues traveling today as the cosmic microwave background. A quiet message from the universe's childhood. The universe was no longer just a hot mixture of energy. It was becoming a place where structures could form. gravity began shaping the future. Small differences in density became increasingly important. Tiny regions with slightly more matter attracted more material. Over millions of years, these regions grew. The first stars formed. The first galaxies appeared. The universe slowly transformed from a simple beginning into a place filled with breathtaking complexity. This transformation is one of the most beautiful stories in science. The universe did not instantly create everything. It evolved. It changed. It developed. The cosmos itself went through a long journey. Much like a seed growing into a forest, the universe started from a simple beginning and gradually created incredible diversity. Astrophysics also reveals something fascinating about the expansion of the universe. Everything is moving away from everything else on the largest scales. Galaxies are not simply traveling through a fixed space. The space between galaxies is expanding. This discovery came from observing that distant galaxies appear shifted toward longer wavelengths of light, a phenomenon known as redshift. The farther away a galaxy is, the faster it appears to move away from us. This does not mean Earth is the center of the universe. Every observer in every galaxy would see the same general pattern. From any location, distant galaxies appear to be moving away because the universe itself is expanding everywhere. There is no special center. The entire universe participates in the expansion. This idea is difficult to imagine because our daily experiences happen on a much smaller scale. We see objects moving through space. We rarely experience space itself changing. But on cosmic scales, the universe behaves in ways that challenge our intuition. The expansion of the universe also raises some of the deepest questions in astrophysics. Will the universe continue expanding forever? Will expansion eventually slow down? Could the universe have a completely different future? Scientists study these questions by observing galaxies, measuring cosmic radiation, and examining the influence of dark matter and dark energy. The answers help us understand not only where the universe came from, but also where it may be going. One fascinating concept connected to the beginning of the universe is cosmic inflation. According to this idea, the early universe may have experienced an extremely rapid expansion during its first tiny fraction of a second. This brief period of incredible growth could help explain why the universe appears so uniform on the largest scales. Regions of space that are now separated by enormous distances share similar properties because they may once have been connected before inflation expanded them apart. Although inflation remains an active area of research, it provides a powerful framework for understanding the earliest moments of cosmic history. The beginning of the universe also reminds us how much remains unknown. Scientists have developed remarkable theories supported by observations. They can describe much of cosmic evolution. They can explain how galaxies formed. They can understand how stars create elements. But the deepest questions remain. What happened at the very first moment? Why did the universe begin with the properties it has? Is our universe the only one? Could there be other universes with different laws of physics? These questions continue inspiring generations of scientists. The beauty of astrophysics is not only found in the answers. It is found in the journey of discovery. Every telescope pointed toward the sky. Every equation written on paper. Every observation collected from distant galaxies. All are attempts to understand our place in this enormous story. And perhaps the most humbling realization is this. The universe spent billions of years evolving before humans appeared. Stars lived and died. Galaxies formed and changed. Planets were created. Eventually, on one small planet around one ordinary star, the universe developed the ability to think about itself. Through human curiosity, the cosmos is studying its own origins. We are not separate observers standing outside the universe. We are part of the universe. The atoms in our bodies were created through cosmic history. The energy that powers our lives comes from ancient processes. The curiosity that leads us to explore the stars is itself a product of billions of years of evolution. The universe created beings capable of wondering about the universe. And that may be one of the most beautiful chapters in the entire story of astrophysics. But our journey is far from over, because beyond the beginning of the universe lies another fascinating mystery, a question that has followed humanity for generations. Are we alone? Could life exist somewhere else among the countless planets scattered throughout the cosmos? To explore that possibility, we must travel into one of the most exciting fields of astrophysics, the search for life beyond Earth. Among all the mysteries explored by astrophysics, perhaps none captures human imagination quite like the possibility of life beyond Earth. For thousands of years, people have looked at the stars and wondered, are there other worlds out there? Are there oceans beneath distant skies? Could another planet somewhere in the universe have watched its own stars rise and set? Could there be another place where someone or something is looking back at the universe with the same curiosity? These questions connect science with one of humanity's oldest dreams. The search for life beyond Earth is not simply a search for another planet. It is a search for understanding our place in the cosmos. Astrophysics has shown us something extraordinary. The universe is enormous beyond imagination. There are hundreds of billions of galaxies. Each galaxy contains billions of stars, and many stars have planets. The number of possible worlds is so large that it is difficult even to comprehend. For much of human history, planets beyond our solar system were only ideas. Scientists could imagine them. Philosophers could discuss them, but there was no direct evidence. That changed with the discovery of exoplanets. Exoplanets are worlds that orbit stars outside our solar system. The first confirmed discoveries transformed our understanding of the universe. Earth was no longer the only known place with planets. Instead, planets appear to be common. They were everywhere. Some orbit extremely close to their stars, completing a year in only a few Earth days. Others travel around their stars at enormous distances, taking centuries to complete one orbit. Some are larger than Jupiter. Some are smaller than Earth. Some exist in systems completely unlike our own. The variety of these worlds is one of the greatest discoveries in modern astrophysics. The universe does not create planets in only one way. It creates countless possibilities. One of the most important concepts in the search for life is the habitable zone. This is the region around a star where conditions might allow liquid water to exist on a planet's surface. Water is considered essential because on Earth, every known form of life depends on it. But the habitable zone is not a guarantee of life. A planet can be located at the right distance and still be completely different from Earth. Many factors matter: the atmosphere, the planet's geology, its magnetic field, its history, its relationship with its star. Earth is not special because it simply exists in the right location. It is special because billions of years of complex processes created a world capable of supporting life. Mars is one of the closest examples of another world that may once have had conditions suitable for life. Today, Mars is cold and dry, but evidence suggests that ancient Mars had flowing water. Rivers carved valleys. Lakes may have existed. Minerals formed in environments where water was present. Scientists continue studying Mars because its ancient history may reveal whether life could have developed elsewhere. The icy moons of the outer solar system also provide fascinating possibilities. Europa, one of Jupiter's moons, is covered by a thick shell of ice. Beneath that frozen surface may exist a global ocean of liquid water. The hidden ocean could contain more water than all of Earth's oceans combined. Scientists wonder whether the conditions beneath Europa's ice could support some form of life. Another intriguing world is Enceladus, a small moon of Saturn. It appears to have an underground ocean, and powerful jets of water vapor and ice particles erupt from its surface. Spacecraft observations have detected molecules that suggest complex chemistry may be occurring beneath its icy exterior. These discoveries show that places once considered frozen and lifeless may actually contain environments where life could potentially exist. The search for life is not limited to our solar system. Astronomers study the atmospheres of distant exoplanets by analyzing starlight passing through them. When a planet crosses in front of its star, a tiny amount of starlight passes through the planet's atmosphere. The chemical fingerprints left behind can reveal what gases are present. Scientists search for combinations of gases that might suggest biological activity. Oxygen, methane, water vapor, other molecules. None of these alone proves life exists, but together they may provide important clues. This method represents one of the most exciting possibilities for future astronomy. One day, advanced telescopes may analyze the atmosphere of an Earth-like planet orbiting a distant star and reveal signs of chemistry unlike anything we have discovered before. The search for extraterrestrial life also raises a fascinating question called the Fermi paradox. The universe appears to contain countless opportunities for life. So why have we not found clear evidence of advanced civilizations? This question has many possible explanations. Perhaps intelligent life is extremely rare. Perhaps civilizations do not survive long enough to communicate across the stars. Perhaps the distances between civilizations are simply too enormous. Or perhaps we are searching in the wrong way. The universe is vast. Even sending a message across our own galaxy would require thousands of years. Communication between distant worlds is not like sending a quick message across Earth. Space creates enormous challenges, yet humanity continues searching. Radio telescopes listen for possible signals from distant civilizations. Missions explore nearby worlds. Powerful observatories study planets around other stars. Each effort represents curiosity reaching beyond its own planet. The possibility of life elsewhere also changes the way we view Earth. Our planet is not just a place where life exists. It is a rare and precious environment shaped by countless cosmic events. The elements needed for life were created inside ancient stars. The water on Earth may have connections to the early solar system. The energy supporting life comes from our sun. Our existence is connected to the entire history of the universe. Perhaps somewhere far away, another planet has its own story. Perhaps there are worlds with different skies, different oceans, and different forms of life. Perhaps the universe contains countless experiments in biology and evolution. Or perhaps Earth is one of the rare places where the universe has awakened and become aware of itself. At this moment, we do not know, and that uncertainty is part of the beauty. Astrophysics does not remove the mystery. It gives us better questions. Every discovery expands our understanding while revealing new possibilities. The search for life reminds us that exploration is not only about finding answers. It is about opening our minds to what could exist. And as we continue our journey through the universe, we now turn towards something even more fundamental: the invisible particles that make up everything around us. The tiny building blocks hidden beneath the surface of reality. The world of quantum astrophysics, where the smallest pieces of existence connect with the largest structures in the cosmos. The universe is a place of enormous scale. Galaxies stretch across millions of light years. Stars burn for billions of years. Black holes contain masses beyond ordinary imagination. Yet hidden beneath all these grand structures is another universe. A universe of tiny particles. A universe where the smallest pieces of reality follow rules that seem almost impossible. This is the world of quantum physics. And when quantum physics meets astrophysics, something truly fascinating happens. Scientists begin exploring how the smallest particles can influence the largest structures in existence. At first, the worlds of the very small and the very large seem completely separate. A tiny particle inside an atom feels unrelated to a galaxy containing hundreds of billions of stars. But modern physics has revealed that these two worlds are deeply connected. The universe operates according to the same fundamental rules at every scale. The atoms that form stars, the particles moving through space, the energy created inside galaxies, all are connected through the same laws of nature. To understand this connection, we must first enter the strange world of quantum mechanics. In everyday life, objects seem to have clear positions and predictable behaviors. A planet follows an orbit. A ball follows a path. A wave moves through water. But at the smallest scales, nature behaves differently. Particles do not always act like tiny solid objects. Instead, they can behave like both particles and waves. This idea is known as wave-particle duality. Light itself provides one of the most famous examples. For centuries, scientists debated whether light was a wave or a collection of particles. The answer turned out to be surprising. Light behaves as both. It depends on how we observe it. Another fascinating connection between quantum physics and astrophysics appears in the vacuum of space. For a long time, people imagined empty space as completely empty, a place with nothing inside. But quantum theory suggests something different. Even the emptiness of space may contain tiny fluctuations. Fields may constantly change. Particles may briefly appear and disappear. The vacuum is not truly nothing. It has structure. It has energy. It has activity. This idea connects to some of the biggest mysteries in cosmology, including dark energy. Scientists continue studying whether quantum effects could help explain why the expansion of the universe is accelerating. The answer remains unknown, but the connection between the smallest scales and the largest scales continues to inspire new discoveries. Quantum physics also plays a role in understanding black holes. These objects represent a meeting point between two great theories of modern science. Einstein's theory of gravity describes the large-scale structure of space-time. Quantum physics describes the behavior of the smallest particles. Near the center of a black hole, both theories become important at the same time, but they do not yet fully agree. This is one of the greatest challenges in modern physics. Scientists are searching for a theory that can combine gravity and quantum mechanics into one complete description of reality. Such a theory is often called quantum gravity. Finding it could transform our understanding of the universe. It could explain what happens inside black holes. It could reveal the true nature of space-time. It could even help us understand the earliest moments of the universe. The search for quantum gravity is a reminder that science is always evolving. The greatest discoveries often happen when existing ideas meet their limits. The universe challenges us. We create better questions. We build better instruments. We develop deeper theories. And slowly, our understanding grows. Quantum astrophysics also introduces another fascinating possibility. The idea that the universe may have many hidden dimensions or structures beyond what we directly experience. Some theories suggest that reality could contain more than the 3 dimensions of space and 1 dimension of time that we know. These ideas remain theoretical, but they show how far human imagination can reach when exploring the fundamental nature of existence. The universe continues to surprise us. From the largest galaxies to the smallest particles, every level of reality contains mystery. The more deeply we look, the more connections we discover. A star is not separate from an atom. A galaxy is not separate from particle. Everything belongs to the same cosmic story. Perhaps that is the most beautiful lesson of astrophysics. The universe is not a collection of unrelated pieces. It is one connected system. The light from distant galaxies, the atoms inside your body, the energy flowing through stars, the tiny particles moving through empty space. All are chapters of one enormous story. And as we continue our journey, we now move toward one of the most fascinating questions in modern astrophysics. What is the true shape of the universe? Is space infinite? Does the universe have an edge? Could there be regions beyond what we can ever observe? To explore these mysteries, we must look at the largest picture possible, the structure and geometry of the cosmos itself. When we look into the night sky, it is natural to imagine the universe as an endless ocean surrounding us. Stars appear scattered across darkness. Galaxies seem like distant islands floating through an enormous emptiness. But one of the deepest questions in astrophysics is much more mysterious. What is the true shape of the universe? Does space continue forever? Does the universe have an edge? Could we travel in one direction through space and eventually return to where we started? These questions take us beyond individual stars and galaxies and into the largest possible view of existence, the structure of the universe itself. For thousands of years, humans imagined space in different ways. Some believed the heavens were a giant sphere surrounding Earth. Others imagined an infinite expanse filled with countless worlds. Modern astrophysics has given us a much deeper understanding, but has also revealed even greater mysteries. The universe is not simply a collection of objects placed inside a fixed space. Space itself has a structure. It can expand. It can curve. It can be shaped by the presence of matter and energy. The geometry of the universe is connected to its contents. Stars, galaxies, dark matter, dark energy. Everything influences the overall shape of space-time. One of the important ideas in cosmology is that the universe can have different types of geometry. Scientists often describe these possibilities as flat, open, or closed. A flat universe is one where the rules of ordinary geometry work on the largest scales. Parallel lines would remain parallel. The overall structure would continue expanding without a global curve. An open universe would have a negative curvature, somewhat like a saddle shape. A closed universe would have positive curvature, similar to the surface of a sphere. In a closed universe, traveling far enough in one direction could theoretically bring you back to where you began. However, the universe is not a simple object we can view from the outside. There is no known place outside the universe where we can stand and observe its shape. We are part of the universe we're trying to understand. It is similar to a creature living on the surface of Earth, trying to understand the entire planet without being able to leave it. We study the universe from within. Scientists use observations of ancient light, galaxy distributions, and cosmic structures to understand its geometry. One of the greatest tools for this investigation is the cosmic microwave background. The tiny patterns within this ancient radiation provide clues about the shape of space itself. Measurements suggest that the universe is extremely close to flat on the largest scales. But this does not mean scientists have solved every mystery. The universe may contain structures and properties that are beyond our current ability to detect. Another fascinating concept is the observable universe. The universe may be much larger than what we can see. The reason is simple. Light travels at a limited speed. When we observe distant objects, we're seeing light that has taken millions or billions of years to reach us. There is a limit to how far information can travel within the age of the universe. This creates a cosmic horizon. Beyond this horizon may exist regions that we cannot observe because their light has not had enough time to reach Earth. Those areas may contain more galaxies, more stars, more planets, perhaps completely different structures. We simply do not know. The observable universe is not necessarily the entire universe. It is only the portion we can access through light and other signals. This idea creates a humbling perspective. Everything humanity has ever observed may represent only a small part of a much larger reality. The universe could extend far beyond our imagination. Some theories even suggest the possibility of a multiverse. The idea that our universe may be one of many universes. Perhaps other universes could have different physical properties, different amounts of matter, different forces, different histories. These ideas are fascinating, but they remain theoretical. There is currently no direct evidence confirming the existence of other universes. However, exploring such possibilities helps scientists examine the deepest questions about reality. Why does our universe have the properties it has? Why do the laws of physics allow stars, planets, and life to exist? Are these conditions unique, or are they part of a much larger cosmic landscape? These questions sit at the edge of modern astrophysics. The expansion of the universe also plays a major role in understanding its structure. As space expands, distances between galaxies increase. But expansion does not happen in the same way everywhere. Gravity keeps some structures connected. For example, galaxies within a cluster can remain bound together despite the overall expansion of the universe. Our own galaxy, the Milky Way, is part of a group of galaxies that remain connected through gravity. But on larger scales, the expansion dominates. The universe is constantly changing. The structure we observe today is only one moment in a much longer cosmic story. If we could watch the universe over billions of years, we would see galaxies slowly moving apart, new stars forming, old stars fading, structures evolving. The cosmos is not frozen. It is alive with motion. Another remarkable aspect of the universe is its incredible uniformity. When scientists study extremely distant regions of space, they find that the universe looks surprisingly similar in all directions. The same types of atoms exist. The same basic physical laws appear to operate. The same cosmic patterns emerge. This is known as the cosmological principle. It suggests that on the largest scales, there is no special location in the universe. Earth is not at the center. The Milky Way is not at the center. No galaxy holds a privileged position. We are simply one part of an enormous cosmic structure. This realization represents one of humanity's greatest shifts in perspective. For much of history, humans imagined themselves as central to creation. Modern astronomy revealed a different story. We live on a small planet, orbiting an ordinary star, inside one galaxy among countless galaxies. Yet this does not make our existence meaningless. Instead, it makes our ability to understand the universe even more remarkable. A small part of the universe has developed the ability to study the whole. The universe has become aware of itself through curiosity and exploration. As we continue exploring the structure of the cosmos, we eventually reach one of the most extreme predictions of astrophysics. A future where stars disappear, galaxies fade, black holes slowly transform. A future where the universe reaches its final stages. The possible endings of the cosmos. And to understand where everything may eventually go, we must explore the ultimate fate of the universe. The universe has a beginning. It has a history. And like everything that exists, it may also have a future. For billions of years, stars have been forming, shining, and disappearing. Galaxies have been growing and merging. Planets have been created from ancient cosmic material. But the universe itself is also changing. The question that fascinates astrophysicists is simple yet profound. What will happen to everything in the end? Will the universe continue expanding forever? Will it eventually collapse? Will it transform into something completely different? The answer depends on the mysterious forces shaping the cosmos today. The future of the universe is one of the greatest stories in astrophysics. To understand where everything may go, we first need to understand the balance between gravity and expansion. Since the beginning of the universe, space has been expanding. At first, gravity played a major role. Matter gathered together. Stars formed. Galaxies appeared. Gravity created structure. It brought clouds of gas together and built the cosmic landscape we see today. For a long time, scientists believed gravity would eventually slow the expansion of the universe. Perhaps one day, expansion would stop. Perhaps gravity would reverse the process. Maybe the universe would begin collapsing back into a hot, dense state. This possible ending was called the Big Crunch, a universe returning to a state similar to its beginning. But observations changed this picture. Scientists discovered that the expansion of the universe is accelerating. Something appears to be pushing space apart faster over time. This mysterious influence is known as dark energy. If dark energy continues behaving as scientists currently observe, the universe may continue expanding forever. The future would become a story of increasing distance and gradual fading. At first, the changes would be almost impossible to notice. Millions and billions of years would pass. Stars would continue forming. Galaxies would continue evolving. But eventually, the universe would enter a very different era. The supply of material needed to create new stars would begin decreasing. Gas clouds would become less common. Star formation would slow. The universe would gradually become quieter. The brilliant era of stars would slowly come to an end. Existing stars would continue shining for enormous periods of time. Small stars, especially red dwarfs, may survive for trillions of years because they use their fuel incredibly efficiently. These tiny stars could become some of the final sources of light in the universe. But even stars have limits. Eventually, they too will run out of fuel. The universe would become increasingly filled with stellar remnants. White dwarfs, neutron stars, black holes, objects that represent the final stages of stellar evolution. During this distant future, galaxies would become dark and silent. The familiar night sky would look completely different. Many galaxies visible today would have moved so far away that their light could no longer reach each other. Future observers might see only their own local galaxy group surrounded by darkness. The universe would appear smaller, not because it shrank, but because expansion carried distant galaxies beyond the visible horizon. This future reminds us that the universe we see today is temporary. The beautiful arrangement of galaxies, stars, and cosmic structures is one moment in a much longer story. Even the stars themselves are temporary. They shine for a while. They transform. They leave behind something new. The universe is constantly changing. One possible ending of the universe is called heat death. Despite its name, this does not mean the universe becomes extremely hot. Instead, it refers to a state where energy becomes evenly spread throughout space. No significant differences in temperature remain. No concentrated sources of energy exist to power complex processes. Stars cannot form. Life cannot continue. The universe approaches a state of maximum calm. A quiet cosmos with almost no activity. This idea may seem sad, but there is something peaceful about it. The universe would not end with a dramatic explosion. It would slowly fade, a long, gentle transition into stillness. However, scientists continue studying whether this is truly the final outcome. Our understanding of dark energy remains incomplete. If its behavior changes over time, the future of the universe could be very different. Another possibility is known as the Big Rip. In this scenario, dark energy would become increasingly powerful. Eventually, the expansion of space could overcome gravitational forces holding galaxies, stars, planets, and even atoms together. The universe would not simply expand. It would tear itself apart. However, current observations do not provide evidence that this will happen. It remains one possible theoretical future. Another possibility involves a change in the nature of dark energy itself. Perhaps it is not constant. Perhaps it evolves. Perhaps our current understanding is only an early step toward a deeper explanation. The universe has surprised scientists before. The future may contain discoveries that completely change our predictions. There's also something fascinating about the timescales involved. The future of the universe is measured not in years or centuries. It is measured in millions, billions, and trillions of years. A trillion years is longer than the entire history of human civilization by an unimaginable amount. Astrophysics teaches us to think beyond ordinary time. It expands our sense of existence. Our lives are brief moments in a much larger cosmic story. Yet those brief moments are enough for us to understand parts of that story. We can study ancient light. We can observe distant galaxies. We can predict possible futures. A small species on a small planet has learned to think about the destiny of the entire universe. That ability is extraordinary. The ultimate fate of the universe also connects to one of the deepest questions in science. What does it mean for something to exist? The universe began with simple conditions. Over billions of years, it created stars, planets, chemistry, and life. Eventually, it produced minds capable of asking questions about its own origin and future. Perhaps the story of the universe is not only about matter and energy. Perhaps it is also about the emergence of awareness. The universe started as a simple beginning. It became a place of incredible complexity. And for a brief moment in cosmic time, it became capable of looking back at itself. As we continue our journey through astrophysics, we now turn toward one of the most mysterious regions in the cosmos. Places where gravity becomes so powerful that nothing, not even light, can escape. Objects that challenge our understanding of space and time. The incredible worlds known as black holes. Among all the wonders of astrophysics, few objects capture the imagination like black holes. They are places where gravity becomes so powerful that the normal rules of our everyday experience begin to break down. They are invisible, yet they can shape entire galaxies. They cannot be seen directly, yet their presence can be discovered through their effects on surrounding matter. They represent some of the most extreme environments in the universe. A black hole is not simply a giant empty hole in space. It is a region where an enormous amount of mass has been compressed into a very small area. The gravity becomes so intense that there is a boundary beyond which escape is impossible. This boundary is called the event horizon. Once anything crosses the event horizon, there is no known way to return. Not a spacecraft, not a particle, not even light itself. That is why black holes appear completely dark. They do not shine like stars. They do not reflect light. They hide themselves from direct observation. Yet the universe reveals their existence through the influence they have on everything around them. The story of black holes begins with some of the most massive stars in existence. When a giant star reaches the end of its life, it may no longer have enough energy to support itself against gravity. The core collapses. If the remaining core is massive enough, even the pressure that supports neutron stars cannot stop the collapse. The result is a black hole. A star that once illuminated the universe becomes an invisible region of extreme gravity. The transformation is one of the most dramatic events in astrophysics. The birth of a black hole is not the disappearance of matter. The matter remains, but becomes compressed into a state where gravity dominates everything around it. The concept of black holes was predicted through Einstein's theory of general relativity. The equations showed that massive objects could create extreme distortions in space-time. At first, many scientists considered black holes to be only mathematical possibilities. The idea seemed too strange. Could nature really create objects where space and time themselves become so distorted? Over time, observations revealed that black holes are not just theoretical ideas. They are real parts of our universe. One of the ways scientists detect black holes is by observing their effect on nearby stars. Imagine a star moving through space with an invisible companion. The star appears to orbit something that cannot be seen. By studying the star's motion, astronomers can calculate the mass of the hidden object. If the mass is too large to be explained by a normal star, the invisible object may be a black hole. Another clue comes from material falling toward black holes. Black holes themselves do not produce light, but the material surrounding them can become incredibly bright. Gas and dust can form a swirling structure called an accretion disk. As a material moves closer to the black hole, it accelerates and heats up. The temperatures can become so extreme that the disk releases powerful radiation, including X-rays. These glowing disks allow scientists to study black holes from across enormous distances. Some black holes are surrounded by enormous jets of energy. These jets can extend thousands or even millions of light years into space. They are created by complex interactions involving magnetic fields, rapidly moving material, and the rotation of the black hole and its surrounding disk. The energy released by these jets can influence entire galaxies. A black hole can be invisible, yet it can shape the evolution of the universe around it. At the center of many large galaxies, including our own Milky Way, scientists believe there is a supermassive black hole. These objects are completely different in scale from black holes created by dying stars. A stellar black hole may contain several times the mass of the Sun. A supermassive black hole can contain millions or even billions of times the mass of the Sun. The supermassive black hole at the center of the Milky Way is called Sagittarius A star. It is located approximately 26,000 light years away from Earth. Although enormous, it does not pose a threat to our solar system because of that vast distance. Its gravity helps influence the movement of stars near the center of our galaxy. Supermassive black holes are among the most mysterious objects in existence. Scientists are still studying how they became so large. Did they begin as smaller black holes that slowly grew? Did enormous clouds of gas collapse directly into them? Did early galaxies and black holes evolve together? These questions remain open areas of research. One of the strangest aspects of black holes is their relationship with time. According to Einstein's theory, gravity affects the passage of time. Near a black hole, time passes differently compared with regions farther away. For an observer approaching a black hole, time would appear normal from their own perspective. But someone watching from a great distance would see their movements appear slower and slower as they approach the event horizon. This effect is called gravitational time dilation. Black holes are also connected to some of the deepest mysteries in physics. At the center of a classical black hole lies a region called a singularity. According to current equations, the singularity represents a point where density becomes infinite and our known understanding of physics breaks down. But many scientists believe this does not mean nature truly contains infinite density. Instead, it may indicate that our theories are incomplete. A complete understanding of black holes may require a theory that combines gravity with quantum physics. This is one of the greatest challenges in modern science. Black holes also revealed something surprising about information and the laws of physics. For many years, scientists debated what happens to information that falls into a black hole. Does it disappear forever, or is it preserved in some way? This question, known as the black hole information paradox, remains one of the most fascinating puzzles in theoretical physics. It suggests that black holes are not just astronomical objects. They may hold clues about the fundamental nature of reality itself. Despite their reputation as destructive objects, black holes are also creative forces in the universe. They influence how galaxies form. They regulate the growth of massive galaxies. They release energy that affects the surrounding environment. They are part of the cosmic ecosystem. The universe does not create objects that are simply good or bad. It creates processes. It creates interactions. It creates change. Black holes remind us that even the darkest places in the universe can reveal some of the brightest discoveries. They challenge our imagination. They test our understanding. And they invite us to continue exploring. Because beyond black holes lies another fascinating mystery. The possibility that the universe may contain hidden bridges through space and time. Theoretical tunnels connecting distant regions of the cosmos. Structures that could reveal new secrets about the nature of reality. The mysterious idea of wormholes. Among the many strange possibilities explored in astrophysics, few ideas are as fascinating as wormholes. They sound like something from a science fiction story. Hidden tunnels through space. Shortcuts connecting distant places. Possible pathways through the fabric of the universe. But the idea of wormholes does not come only from imagination. It comes from the mathematics of Einstein's theory of relativity. When scientists study the equations describing space-time, they discover that under certain conditions, the structure of the universe could allow unusual connections. These hypothetical tunnels are known as wormholes. A wormhole can be imagined as a bridge through space-time. Instead of traveling across the enormous distance between 2 points, a traveler could theoretically take a shortcut through a different path. Imagine a piece of paper with 2 dots drawn far apart. If you travel across the surface, the journey takes a long time. But if you fold the paper so the 2 dots touch, you could create a shortcut between them. A wormhole is a similar concept applied to the fabric of space-time. It is important to remember that wormholes have not been discovered. There is currently no evidence that they exist in our universe. They remain theoretical possibilities created from mathematical solutions. But studying them helps scientists understand the possibilities and limitations of space and time. The first serious discussions of wormholes appeared after Einstein developed general relativity. His equations showed that massive objects could curve space-time. Later scientists explored whether these curves could connect different regions of the universe. One early example was the Einstein-Rosen bridge. It suggested a possible connection between different parts of space-time. However, these early ideas did not describe wormholes that could be safely traveled through. They were more like mathematical structures rather than cosmic tunnels. Modern theories explore more complex possibilities. Some researchers have investigated whether stable wormholes could exist. The challenge is enormous. A wormhole would likely collapse instantly unless something could hold it open. Theoretical physics suggests that a substance with unusual properties, sometimes described as negative energy, might be required. However, we have never found enough of such material to create or stabilize a wormhole. Nature may allow the mathematics of wormholes without allowing them to exist as practical cosmic tunnels. This distinction is important in science. A mathematical possibility does not always become a physical reality. The universe has many ideas that work on paper but may never appear in nature. Even so, wormholes raise some of the deepest questions about reality. Could distant parts of the universe be connected? Could space have hidden pathways? Could time itself be affected by these structures? These questions push scientists to examine the foundations of existence. Wormholes are also connected to the idea of time travel. If one end of a wormhole experienced time differently from the other end, some theoretical models suggest that it could create a path between different moments in time. However, This idea creates many complicated problems. The laws of physics may prevent such situations from occurring. There are also questions about causality. If someone could travel backward in time, could they change events that already happened? Could they create contradictions? These questions have fascinated scientists and philosophers for decades. While wormholes remain speculative, they provide a valuable way to explore the limits of our understanding. They show us where our current theories become uncertain. They encourage scientists to search for deeper explanations. Perhaps one day, a future theory of physics will reveal whether wormholes are only mathematical possibilities or actual features of the universe. The universe has surprised us before. Black holes were once considered impossible. Gravitational waves were once only predictions. Exoplanets were once ideas without evidence. Many discoveries began as strange possibilities before becoming accepted parts of science. Wormholes remind us to keep an open mind while respecting evidence. The universe is far more complex than human intuition suggests. Space is not simply a fixed, empty background. It is dynamic. It can expand. It can curve. It can carry waves. It may contain structures we have not yet discovered. The study of wormholes also connects with one of astrophysics' greatest goals, understanding the complete nature of space-time. Einstein's theory explains gravity beautifully on large scales. Quantum physics explains the behavior of tiny particles. But combining these two descriptions remains one of the biggest challenges in science. Perhaps the deeper theory that unites them will reveal new insights about wormholes, black holes, and the origin of the universe itself. For now, wormholes remain among the universe's most beautiful mysteries. They represent humanity's desire to explore. They show how curiosity can travel beyond what we can currently reach. Even if we never find a real wormhole, the questions they create have already expanded our understanding of reality. The universe is not only a place of objects, it is a place of possibilities. And sometimes, the most important discoveries begin with a simple question. What if? What if space has hidden connections? What if reality contains structures beyond our imagination? What if there are parts of the universe waiting to be discovered? These questions continue guiding astrophysics forward. And as we continue our journey through the cosmos, we now turn toward another mysterious phenomenon that affects some of the most powerful objects in the universe. The invisible waves that travel through the fabric of reality itself. The cosmic vibrations created by the movement of massive objects. The incredible phenomenon known as gravitational waves. Across the universe, everything is moving. Galaxies drift through space. Stars orbit within galaxies. Planets circle their suns. Even space itself expands and changes. For centuries, humans could only observe the universe through light. The stars told their stories through visible rays. The galaxies revealed their secrets through radio waves, X-rays, and other forms of radiation. But the universe had another language waiting to be discovered. A language written not in light, but in the movement of space-time itself. This language is carried by gravitational waves. Gravitational waves are tiny ripples traveling through the fabric of space-time. They are created when massive objects accelerate through space. The most powerful sources are some of the universe's most extreme events. Two black holes spiraling toward each other. Two neutron stars colliding. Massive stars exploding. When these enormous objects move, they create waves that spread outward at the speed of light. For billions of years, These waves traveled silently across the universe. They passed through galaxies. They crossed empty regions of space. They carried information about events that happened long before humans existed. Then, in 2015, humanity detected gravitational waves for the first time. The signal came from two black holes merging over 1 billion light-years away. The discovery opened a completely new way of exploring the cosmos. It was like gaining a new sense. Before gravitational wave astronomy, humans studied the universe mostly through sight. Now we could also listen. The universe was no longer silent. It was creating cosmic vibrations that carried stories from the deepest regions of space. Gravitational waves are incredibly difficult to detect because they're extremely weak by the time they reach Earth. The stretching and squeezing they create is unbelievably small. Scientists built some of the most sensitive instruments ever created to measure these tiny changes. These observatories can detect movements smaller than the size of an atomic nucleus. The precision required is almost impossible to imagine. Yet through patience, technology, and curiosity, humans were able to hear the universe in a completely new way. The discovery of gravitational waves confirmed another prediction of Einstein's theory of relativity. More than 100 years after he developed his ideas, the universe provided another piece of evidence supporting his understanding of space-time. This is one of the beautiful patterns in science. Ideas begin as mathematics. They become predictions. Then, many years later, nature reveals whether they are correct. The universe becomes the ultimate experiment. Gravitational waves also allow scientists to study objects that are otherwise difficult to observe. Black holes do not release light directly, but when two black holes merge, the gravitational waves created during the collision reveal their presence. Scientists can measure their masses. They can understand how they move. They can study how space-time behaves under extreme conditions. Every detection adds another chapter to our understanding of the universe. The future of gravitational wave astronomy is incredibly exciting. New observatories planned for space may detect even lower frequency waves created by enormous cosmic events. These future instruments could observe merging supermassive black holes at the centers of galaxies. They could reveal information about the earliest moments of cosmic history. They could uncover phenomena we have never imagined. The universe may contain signals waiting patiently for us to discover them. Gravitational waves remind us that the cosmos is not just a collection of objects. It is an active environment. Space itself can move. Space itself can carry information. The universe is not a silent emptiness. It is a constantly changing ocean of energy and motion. And as we continue exploring the largest structures in existence, we encounter another breathtaking pattern. A vast network connecting galaxies across unimaginable distances. A structure so enormous that it stretches across hundreds of millions of light years. The cosmic web. The universe may appear random when we look at individual stars, but on the largest scales, it reveals a hidden organization. Galaxies are arranged along enormous invisible pathways. These pathways form a structure resembling a giant web spread throughout space. This is known as the cosmic web. The cosmic web is one of the greatest achievements of gravity over billions of years. It began with tiny differences in the early universe. Small regions contained slightly more matter than others. Gravity slowly pulled additional material toward these regions. Over time, these areas grew. The simple patterns of the early universe became enormous structures containing galaxies, clusters, and vast empty spaces. The cosmic web contains filaments. These are long structures where galaxies gather. Between them are enormous voids where very little matter exists. The contrast is remarkable. Some regions of space are filled with countless galaxies. Others stretch across millions of light years with almost nothing inside. The universe creates both abundance and emptiness. The invisible influence of dark matter plays a major role in creating this structure. Before ordinary matter gathered into galaxies, dark matter formed the underlying framework. It acted like an invisible skeleton. Gas and stars later followed these structures, creating the cosmic patterns we observe today. When astronomers map galaxies across enormous distances, they see this web-like arrangement. It is one of the strongest examples of how invisible forces shape visible reality. The cosmic web also shows how connected the universe truly is. A galaxy millions of light years away is not completely isolated. It belongs to a larger structure. It exists along pathways shaped by gravity. Every galaxy is part of a much greater cosmic story. The web is still changing today. Galaxies continue moving. Clusters continue interacting. Gravity continues shaping the universe. The cosmos is not finished forming. It is still evolving. And perhaps one of the most beautiful discoveries is that our own galaxy is part of this enormous structure. The Milky Way is not alone. It belongs to a small group of galaxies connected through gravity. It has a history stretching back billions of years. A history filled with collisions, transformations, and cosmic memories. To understand our place in the universe, we must now journey closer to home, toward the galaxy we call our own, the Milky Way. When we look at the night sky, we are looking into our own cosmic home. Among the countless galaxies scattered throughout the universe, there is one that holds everything familiar to us. The stars we see from Earth, the planets of our solar system, the ancient clouds of gas and dust that created generations of stars. This is the Milky Way galaxy, a vast spiral of light, darkness, and mystery. The Milky Way is enormous beyond human imagination. It contains hundreds of billions of stars, along with countless planets, clouds of gas, dust, and invisible dark matter. Yet from Earth, we see only a small part of its true size. Our galaxy stretches across more than 100,000 light years. If we could travel at the speed of light, it would take over 100,000 years to cross from one side to the other. The Milky Way is not just a collection of stars. It is a living cosmic structure that has evolved over billions of years. Its story began in the early universe. After the first stars formed, gravity slowly gathered groups of stars and gas together. Small galaxies formed. Over immense periods of time, these galaxies merged and grew. The Milky Way was created through this long process of cosmic evolution. Our galaxy carries memories of its ancient past. Hidden within its stars are clues about previous generations. Some stars contain elements created inside stars that lived and died billions of years ago. By studying these ancient stars, astronomers can reconstruct the history of the Milky Way. It is like reading the pages of an ancient book written in starlight. The Milky Way has a beautiful spiral structure. From above, it would appear like a giant spinning pinwheel with curved arms extending outward. These spiral arms are regions where stars, gas, and dust gather. They are also places where new stars are born. Inside these enormous clouds of gas, gravity slowly pulls material together. Over time, temperatures rise, pressure increases. Eventually, a new star begins shining. The galaxy is constantly creating new generations of stars. But the Milky Way is also a place of endings. Older stars eventually run out of fuel. Some become white dwarfs. Some explode as supernovae. Some collapse into neutron stars or black holes. The galaxy is a cycle of creation and transformation. Nothing remains unchanged forever. At the center of the Milky Way lies one of the most mysterious objects in existence. A supermassive black hole known as Sagittarius A star. It contains millions of times the mass of the Sun. Although enormous, it is located far away from Earth, and its gravity does not threaten our solar system. Instead, it helps astronomers study how galaxies evolve. Many large galaxies appear to contain supermassive black holes at their centers. This suggests that galaxies and black holes may have developed together throughout cosmic history. The relationship between them remains one of the fascinating questions in astrophysics. The Milky Way also contains enormous clouds of gas and dust called nebulae. These regions are some of the most beautiful structures in space. They are often described as cosmic nurseries because they create new stars. Inside these clouds, tiny particles slowly gather. Gravity begins its work. A new star begins forming. A new chapter begins. The same process that created our sun billions of years ago continues happening throughout the galaxy today. The Milky Way is also surrounded by a massive halo of dark matter. Although we cannot see this invisible substance, scientists can observe its gravitational influence. Without dark matter, the motion of stars within the galaxy would not match what we observe. The galaxy we see is only part of the larger structure surrounding it. There is a hidden galaxy beneath the visible one, a galaxy made of invisible mass. The Milky Way is also moving through space. Our galaxy is part of a group called the Local Group, which contains several galaxies connected by gravity. Over billions of years, galaxies within this group interact. In the distant future, the Milky Way will experience a dramatic encounter with the Andromeda Galaxy. These two enormous galaxies are moving toward each other. Eventually, they will merge. Although the word collision sounds destructive, galaxies are mostly empty space. Individual stars rarely crash into each other. Instead, the two galaxies will slowly combine, creating a new galaxy with a different shape and structure. This event reminds us that galaxies are not permanent. They change, they grow, they transform. The Milky Way also provides humanity with a unique perspective. From Earth, we can observe the galaxy from inside it. The glowing band of stars stretching across the night sky is actually the view toward the crowded center of our galaxy. Ancient civilizations looked at this mysterious band of light and created stories about it. Today, science reveals a deeper story. That faint glow represents billions of stars located across an enormous cosmic landscape. The Milky Way is our home, but it is only one galaxy among countless others. There are galaxies larger than ours, smaller than ours, galaxies with different shapes, galaxies with different histories. Yet every galaxy shares a similar story. Gravity brings matter together. Stars are born. Stars transform. Elements spread through space. New worlds emerge. The universe constantly rebuilds itself. Our own existence is connected to this process. The atoms that make our bodies were created inside ancient stars that existed before the sun and Earth. The oxygen we breathe, the carbon in our cells, the minerals inside our planet, all carry the history of cosmic evolution. We are not visitors to the universe. We're made from it. The Milky Way reminds us of something profound. Even though we live on a tiny planet around one ordinary star, we are connected to an enormous cosmic structure. Our story is part of the galaxy's story, and the galaxy's story is part of the universe's story. As we continue our journey through astrophysics, we now travel backward to another important chapter. Before stars existed, before planets formed, before our solar system was born, a time when a cloud of gas and dust began the process that would eventually create our home. The birth of the solar system, before Earth had oceans, before the sun had planets orbiting around it, before the first sunrise touched our world. There was only a vast cloud of gas and dust drifting silently through space, a place where the ingredients for a future solar system were waiting. The birth of our solar system began approximately 4.6 billion years ago. It started with a giant molecular cloud. These clouds are enormous collections of cold gas and tiny particles floating between stars. They are some of the quietest places in the universe. But within these peaceful clouds, gravity can slowly begin creating something extraordinary. A small disturbance caused part of the cloud to become slightly denser. Perhaps a nearby star exploded. Perhaps waves from another region of the galaxy passed through. Whatever the cause, gravity began pulling material inward. The cloud started collapsing. As it collapsed, it began spinning. The material gathered into a rotating disk. At the center of this disk, pressure and temperature increased until nuclear fusion began. The first light of our sun appeared. A new star was born. Around the young sun, leftover material continued moving through space. Tiny particles collided and stuck together. Over millions of years, these small pieces grew larger. They became rocks, then larger bodies, then the first building blocks of planets. This process is called accretion. The solar system was not created instantly. It was assembled slowly through countless collisions and transformations. The inner region near the sun was extremely hot. Only materials that could survive high temperatures remained. This is why the inner planets, Mercury, Venus, Earth, and Mars, are mostly rocky worlds. Farther away from the sun, temperatures were colder. Ice and gases could survive. This allowed the outer planets to become much larger. Jupiter and Saturn grew into enormous gas giants. Uranus and Neptune became distant worlds rich in ice and gas. Each planet carries the history of where it formed. Earth itself began as a young, violent world. Its surface was constantly changing. Asteroids and other objects collided with it. Volcanoes released gases. The planet slowly transformed. Eventually, conditions became suitable for oceans, atmosphere, and life. The story of Earth is connected to the story of the entire solar system. The water on our planet may have connections to ancient icy objects that traveled through space. The elements inside Earth were created through cosmic processes that happened long before our sun existed. Our planet is a piece of a much larger history. The solar system also contains countless smaller objects. Asteroids, comets, dust particles. These objects are reminders of the early days of planetary formation. Asteroids are ancient leftovers from the time when planets were forming. They preserve materials that have changed very little over billions of years. By studying asteroids, scientists can learn about the conditions that existed when the solar system was young. Comets tell another fascinating story. They are frozen objects containing ice, dust, and ancient chemicals. When they approach the sun, heat causes them to release gas and dust, creating their beautiful glowing tails. For thousands of years, humans watched these mysterious visitors appear in the sky. Today, spacecraft travel directly to comets to study them. They're like time capsules from the beginning of our cosmic neighborhood. The solar system is also a place of incredible diversity. Mercury experiences extreme temperatures because it has almost no atmosphere to protect it. Venus has a thick atmosphere that creates a powerful greenhouse effect, making it the hottest planet in our solar system. Mars contains the largest volcano known in the solar system and evidence that ancient water once flowed across its surface. Jupiter possesses enormous storms that have lasted for centuries. Saturn's rings create one of the most beautiful sights in astronomy. The distant ice giants reveal worlds unlike anything found near Earth. Each planet tells a different story. Each world represents a different experiment created by nature. The solar system also teaches us that planets are not always peaceful places. Space is filled with collisions, radiation, and powerful forces. Worlds change over time. Some lose their atmospheres. Some become frozen. Some experience dramatic geological activity. The universe is constantly reshaping itself. Even today, our solar system is not finished evolving. Asteroids continue moving. Comets continue traveling. The sun continues changing. One day, billions of years from now, the sun itself will enter the final stages of its life. It will expand into a red giant. Its outer layers will drift away. The solar system we know today will transform into something completely different. Yet the atoms created by the sun and planets will continue traveling through space. The universe does not truly erase anything. It transforms. The story of the solar system also leads us to a deeper realization. Our planet is not separate from the universe. It is a natural result of cosmic evolution. The same laws that create stars also create planets. The same elements found in distant galaxies exist here on Earth. The same processes that shaped the universe shaped our home. We are part of the same cosmic journey. As we reach the final chapters of our exploration, we return to the biggest questions. Not only how the universe works, but what it means that we are here to observe it. The universe is filled with mysteries. There are questions scientists can answer. There are questions waiting for future discoveries. And there are questions that may remain mysteries for generations. But perhaps the most beautiful part of astrophysics is not knowing everything. It is having the curiosity to continue searching. Every telescope pointed toward the stars represents humanity's desire to understand. Every discovery reveals something new. Every answer creates another question. The universe is a story without a final page. From the first moments after the Big Bang to the birth of stars. From ancient galaxies to planets capable of supporting life. From invisible particles to enormous cosmic structures. Everything is connected. The universe created stars. Stars created elements. Elements created planets. Planets created life. And life became capable of looking back at the universe and asking why it exists. In a quiet corner of the cosmos, on a small planet orbiting an ordinary star, the universe became aware of itself. That may be one of the greatest mysteries of all. Not the size of galaxies, not the power of black holes, not the age of the universe, but the simple fact that the universe produced beings who can wonder about it. So as you rest tonight, remember that you are connected to something far greater than yourself. The atoms inside you were created in ancient stars. The energy around you comes from a universe billions of years old. The curiosity in your mind is part of the same cosmic story that began long before Earth existed. Above you are countless stars. Beyond them are countless galaxies. Beyond what we can see may be countless more wonders waiting to be discovered. The universe is vast. The universe is mysterious. And the universe is still telling its story. Thank you for joining this peaceful journey through astrophysics. Allow your thoughts to become quiet. Allow the images of distant stars, galaxies, and cosmic wonders to slowly fade into the background. Let the universe continue its endless journey while you rest. Good night, and may your dreams travel peacefully through the stars.